What if everything you thought you knew about the universe was just the tip of the iceberg? Picture this: a cosmic tapestry where gravity isn't just a force, but a warp in the very fabric of space and time, where massive objects don't just pull on each other, but actually bend the stage on which reality plays out. This isn't science fiction. It's the startling truth revealed by decades of groundbreaking experiments probing space-time curvature, a phenomenon so profound it reshapes how we understand existence itself. From the echoes of colliding black holes to the eerie behavior of particles at the quantum edge, scientists have devised astonishing ways to test the limits of Einstein's theories, and what they've found will leave you in awe. Think about the last time you dropped a ball. It fell to the ground, simple as that. But what if I told you that ball wasn't just obeying gravity? It was following a curve in space-time created by Earth's immense mass. That's the essence of space-time curvature, a concept so revolutionary it turned physics upside down. Yet for all its elegance, Einstein's theory of general relativity left us with tantalizing gaps, places where the math breaks down, where the rules seem to vanish into the unknown. That's where these 42 ingenious experiments come in. They're not just tests, they're voyages into the unexplored, each one peeling back another layer of the cosmos' deepest secrets. Why should you care? Because this isn't just about equations or abstract ideas. It's about uncovering the hidden blueprint of the universe, the invisible architecture that shapes everything from the orbits of planets to the fate of galaxies. Some of these experiments span continents, using lasers and mirrors to catch ripples in space-time itself. Others happen in labs so precise they can measure distortions smaller than an atom. And then there are the ones that venture into realms so strange they challenge our very notion of reality. So buckle up. Over the next hour, we'll journey through triumphs of human curiosity that have brought us face to face with the universe's greatest mysteries. And trust me, by the end, you'll never look at the night sky the same way again. The story of space-time curvature leaped from theory to reality in 1959, when two physicists at Harvard University performed an experiment so precise it bordered on the impossible. Robert Pound and Rebka aimed to test one of Einstein's boldest claims, that light climbing against gravity would lose energy, its wavelength stretching like taffy pulled upward. They turned a 22.6-meter-tall tower into a cosmic laboratory, firing gamma rays from the bottom to the top and measuring the faintest whisper of a frequency shift. The difference they expected was vanishingly small, just 2 parts in a quadrillion, yet their results matched Einstein's prediction with stunning accuracy. For the first time, humanity had proof that gravity doesn't just bend light's path, it warps light itself. But here's where it gets even wilder. That redshift wasn't just about light, it revealed something far deeper. If gravity alters light's frequency, it means time itself must be stretching. Think of it like this: a clock at the base of that tower, closer to Earth's mass, would tick slower than 1 at the top, just as Einstein's equations foretold. This phenomenon, called gravitational time dilation, isn't some abstract quirk. It's the reason your GPS doesn't lead you into a lake. Satellites orbiting high above Earth experience time slightly faster than we do on the surface, and if their clocks weren't constantly corrected for this effect, your navigation would drift off by nearly 7 miles every single day. What's truly mind-bending is how humble this experiment seems compared to its implications. Pound and Rebka didn't need black holes or colliding neutron stars, just a tower, some gamma rays, and relentless curiosity. Their work became a cornerstone for technologies we now take for granted, while also opening the door to even stranger discoveries. Imagine telling them that 60 years later, Their experiment would help calibrate detectors catching ripples from cosmic collisions billions of light years away. It's a reminder that sometimes the universe's grandest truths hide in the subtlest shifts if we're clever enough to look. While Pound-Rebka revealed time bending under gravity's weight, another team set out to prove that speed could stretch time too, and they did it with a handful of atomic clocks and a couple of commercial airliners. The year was 1971, and physicists Joseph Hafele and Richard Keating had a radical idea. If Einstein was right, time should slow down for clocks moving at high speeds. So they packed 4 cesium atomic clocks, devices so precise they lose less than 1 second every 300,000 years, into airplanes flying eastward and westward around the globe. When they compared these jet-setting clocks to ones left stationary on the ground, the results were undeniable. The clocks that had circled Earth weren't just slightly off, they'd experienced time differently, ticking slower by fractions of a second. Here's the twist: the eastbound clocks slowed down more than the westbound ones. That's because Earth itself is rotating eastward, so a plane flying that direction moves even faster relative to the planet's core, amplifying the time warping effect. Meanwhile, the westward plane was fighting Earth's spin, reducing its relative speed. It's like running on a moving walkway. Going with the flow makes you faster against the ground, while going against it cancels out some of your speed. This nuance proved something extraordinary. Time doesn't just bend under gravity, it flexes with motion too. A passenger on those planes aged ever so slightly less than someone staying put, a real-life version of science fiction's twin paradox. But Hafele and Keating's experiment wasn't just about confirming Einstein. It revealed how relativity shapes our everyday world. Today, this effect is factored into everything from satellite communications to stock market trades, where nanoseconds matter. Imagine 2 high-frequency traders, one in New York, one in London, making deals based on atomic clocks. Without accounting for time dilation, their transactions could fall out of sync, potentially costing millions. It's a reminder that the universe's rules don't pause for human convenience. Now, take that same principle and crank it up to cosmic extremes. If a commercial jet can alter time's flow, what happens near a black hole where gravity bends reality to its breaking point? The year 2015 marked a revolution in how we perceive the cosmos, not through telescopes, but through vibrations in the very fabric of reality. The Laser Interferometer Gravitational Wave Observatory, or LIGO, did what even Einstein thought might be impossible. It caught the faint whisper of 2 black holes colliding over 1.3 billion light-years away. These weren't just any black holes, each packed roughly 30 times the mass of our Sun into a space smaller than a city, spiraling toward each other at half the speed of light before merging in a cataclysm so violent it sent ripples through space-time itself. The signal LIGO detected lasted less than half a second, yet it carried more energy than all the stars in the observable universe shining combined for that same fleeting moment. What makes this discovery so extraordinary isn't just the confirmation of gravitational waves. Einstein's math had predicted them a century earlier. It's how these waves rewrite the rules of astronomy. Until LIGO, every cosmic discovery relied on light, visible, radio, X-rays. But gravitational waves are different. They pass through matter unimpeded, carrying pristine information from events light could never escape, like the final moments before 2 black holes become one. It's as if the universe handed scientists a new sense, letting them hear phenomena that were previously invisible. Consider this: when those black holes merged, their gravitational wave signature revealed details no telescope could capture. The pitch and amplitude of the signal betrayed their masses, their spin rates, even the precise distance they traveled before collision. And here's the kicker, this was just the beginning. Since that first detection, LIGO and its European counterpart, Virgo, have spotted dozens more mergers, including neutron stars colliding in a spectacle that also flared across the electromagnetic spectrum. These events aren't just cosmic fireworks, they're cosmic alchemy, forging heavy elements like gold and platinum in their wake. But the real magic lies in what's next. Gravitational waves could unveil secrets about the universe's earliest moments, probing the Big Bang itself. Light from that era was trapped in a dense plasma, but gravitational waves from the birth of the cosmos might still ripple through space today, waiting to be caught by next-generation detectors. There's even speculation about waves from cosmic strings, hypothetical defects in space-time left over from the universe's infancy. Every new detection peels back another layer, proving that sometimes to see the universe clearly, you need to listen. Even the most delicate cosmic phenomena leave fingerprints if you know where to look. In 2004, NASA launched Gravity Probe B, a satellite so precise it could detect space-time twisting around our planet like silk caught in a gentle whirlpool. At the heart of this mission was a concept so subtle Einstein himself doubted we'd ever measure it: frame dragging, the idea that Earth's rotation doesn't just move matter, but drags the fabric of space-time along with it. Picture stirring honey into tea. The spoon pulls the thick liquid into a spiral around it. Now imagine Earth as that spoon, its rotation ever so slightly warping the invisible medium of space-time itself. To catch this effect, Gravity Probe B carried 4 gyroscopes, each a flawless sphere of quartz larger than a golf ball, polished to within 40 atoms of perfection. These gyroscopes were the stillest objects ever created, floating in a vacuum colder than interstellar space. As the satellite orbited, scientists expected Earth's rotation would tug the fabric of space-time around it, causing the gyroscope's spin axis to drift by a hair's width over a year, just 1 degree every 100,000 years. The challenge: measuring shifts smaller than 100,000th of a single degree. It's like tracking the tilt of a skyscraper from orbit, where a millimeter shift at the base becomes invisible from space. After 17 months of painstaking data collection, the results emerged. Space-time around Earth was indeed being dragged, exactly as Einstein's equations predicted. But the real triumph wasn't just confirming the theory, it was the staggering engineering behind it. To cancel out interference from Earth's magnetic field, the satellite used superconducting lead bags. To shield the gyroscopes from solar wind, it flew in near-perfect silence, guided by a custom star tracker locked onto the constellation Pegasus. Every component pushed the boundaries of precision, revealing how even the faintest cosmic whispers demand our most advanced tools. Yet Gravity Probe B's legacy extends beyond frame dragging. Its technology paved the way for GPS enhancements and deep space navigation, while proving that space-time isn't just curved, it's dynamic, responding to motion like a living fabric. Now imagine scaling this up. If Earth's modest spin creates detectable ripples, what happens near a pulsar spinning hundreds of times per second, or a supermassive black hole where space-time isn't just dragged but shredded into chaos? The answer might lie in next-generation probes armed with quantum sensors or atom interferometers, hunting for distortions we've yet to dream of. Here's the humbling truth: Gravity Probe B measured an effect so small, it's like detecting a ripple in a pond light years wide. But in that ripple lies a universe of possibility, proof that reality bends not just to gravity's weight, but to its motion. And if we can hear space-time's faintest murmurs today, what symphonies might we uncover tomorrow? The quantum realm has a way of laughing at our everyday intuition. And nowhere is this more apparent than in the baffling dance of entangled particles. In 2017, a Chinese satellite named Ingenious performed an experiment that would make even Einstein uneasy. Scientists fired pairs of photons-light particles linked through quantum entanglement from space to ground stations separated by a staggering 1,200 kilometers. Here's the twist: measuring one photon instantly affected its partner, no matter the distance. This wasn't just faster than light communication. It was as if space itself didn't exist between them. Einstein famously called this spooky action at a distance, but Ingenious proved it wasn't just spooky, it was real. What makes quantum entanglement so revolutionary isn't just the defiance of classical physics. It's the way it hints at a hidden architecture beneath space-time. Think of two entangled particles as a single coin split across the universe. Flip one side to heads, and the other snaps to tails instantly, with no signal traveling between them. This isn't magic, it's a property woven into the fabric of reality itself. The Ingenious satellite didn't just break distance records, it forced us to confront a startling possibility: that space-time, for all its curvature and grandeur, might be just the surface of something far stranger. Now imagine if entanglement isn't just threading through space-time, but around it like shortcuts through hidden dimensions. Some theories suggest these particles aren't communicating faster than light, but bypassing our three-dimensional reality altogether. It's as if the universe has a backstage, and entangled particles are slipping through the curtains. The Ingenious experiments edge us closer to testing these wild ideas. If entanglement truly ignores distance, could it be a window into higher dimensions or the quantum structure of gravity itself? The implications ripple outward. Secure quantum networks, unhackable because any eavesdropping would break the entanglement, are already being built. But the bigger prize might be unifying quantum mechanics with gravity, the holy grail of physics. Black holes, those ultimate space-time warpers, might also be entanglement factories, their event horizons birthing entangled particles in pairs. If we can untangle this knot, we might finally understand how the quantum world's weirdness stitches together the cosmic scale. Ingenious didn't just stretch the limits of entanglement, it stretched our imagination. Every photon pair that defied distance whispered a question: what else is out there, lurking in the quantum shadows of space-time? The answer could rewrite not just physics textbooks, but the very story of reality. For centuries, black holes existed only in equations and imaginations, until April 10, 2019, when humanity stared into the abyss and the abyss stared back. The Event Horizon Telescope didn't just detect a black hole, it captured its shadow against a fiery halo of light, giving us our first visual proof of space-time's ultimate distortion. At the heart of Galaxy Messier 87, 55 million light-years away, a monster weighing 6.5 billion suns revealed itself not by what we could see, but by what we couldn't, a dark void where light itself surrenders to gravity's grip. That iconic orange ring isn't just artistic interpretation. It's the signature of photons skating along the edge of oblivion, their paths bent so severely by the black hole's gravity that they loop around it like cars on a cosmic racetrack. Some light escapes to reach our telescopes, while just beside it, darkness marks the point of no return, the event horizon, where space-time curves so sharply that not even light can climb out. What makes this image revolutionary isn't just its beauty, but its precision. The ring's thickness and asymmetry match Einstein's predictions down to the pixel, proving that even under conditions of extreme gravity, his century-old equations hold sway. But here's what most people miss. That snapshot was technically impossible until we turned Earth itself into a telescope. The Event Horizon Telescope isn't a single instrument, it's a network of 8 radio observatories spanning from Hawaii to the South Pole, synchronized to act as one planet-sized lens. Why? Because resolving a black hole's shadow requires a telescope with a resolution sharp enough to spot a donut on the moon. By combining signals from telescopes thousands of miles apart using a technique called very long baseline interferometry, scientists achieved an angular resolution 50 times finer than the Hubble Space Telescope. The data collected in April 2017 was so vast it couldn't be sent over the internet. Hard drives of observations had to be physically flown to supercomputers in Germany and Massachusetts. Then came 2 years of painstaking reconstruction, where algorithms filled gaps like cosmic detectives reconstructing a crime scene from scattered clues. The result wasn't just an image, it was a time machine. Those photons began their journey when Earth was entering an ice age, and by the time they reached us, we'd built tools to decode their message. Yet this milestone is just the beginning. The same team has since trained their sights on Sagittarius, a star, the supermassive black hole at our galaxy's center. Unlike Messier 87's relatively placid giant, Sagittarius, a star, is a turbulent beast, flickering with X-ray flares as it devours matter. Capturing its portrait could reveal how black holes feed and how their immense gravity orchestrates the dance of stars around them. Future expansions of the telescope array, possibly incorporating space-based antennas, might even resolve the black hole's photon ring, a razor-thin circle of light predicted to orbit just outside the event horizon, where space-time twists like a Möbius strip. What's truly humbling is how this experiment bridges scales. The same curvature that gently guides planets in their orbits becomes, near a black hole, a maelstrom that twists the universe into knots. And in that distortion lies a clue to physics' greatest mysteries, where Einstein's relativity meets the quantum realm, where space-time might not be smooth but pixelated, and where our current laws of physics simply stop. The Event Horizon Telescope didn't just give us a picture, it handed us a key to the universe's most locked doors. Picture the emptiest space you can imagine, a perfect vacuum where not even a single atom lingers. Now brace yourself, because even that void is alive with chaos. In 1948, Dutch physicist Hendrik Casimir predicted something extraordinary. If you place 2 uncharged metal plates incredibly close together in a vacuum, they'd be pushed toward each other by an invisible force. It sounded impossible. How could nothingness exert pressure? Yet 20 years later, experiments proved him right. This phenomenon, now called the Casimir effect, reveals that the vacuum of space isn't empty at all. It's a seething quantum ocean where particles flicker in and out of existence so fast we can't see them, like bubbles boiling in a cosmic pot. Here's the catch. Quantum mechanics allows these virtual particles to borrow energy from the universe for impossibly brief moments, creating a turbulent foam at scales smaller than atoms. Normally, particles and antiparticles annihilate each other too quickly to notice, but squeeze them between 2 plates spaced just nanometers apart, and something wild happens. Only certain wavelengths of virtual particles can fit in that gap, while outside the plates, all wavelengths thrive. This imbalance creates a pressure differential, like placing a narrow hallway between 2 crowded rooms and suddenly feeling the walls buckle from the difference in noise. The result, the plates snap together as if tugged by an unseen hand. What's mind-blowing isn't just the force itself, it's what it implies about reality. The Casimir effect suggests that space-time, which looks smooth and serene through telescopes, is actually a stormy quantum sea at microscopic scales. Imagine flying over an ocean on a calm day. From high above, the water seems flat and still, but drop down to the surface and you're surrounded by churning waves. That's the difference between Einstein's curved space-time and the frothing quantum realm beneath it. This discovery isn't just theoretical curiosity. Engineers now grapple with the Casimir effect in nanotechnology, where tiny machinery can stick together unpredictably because of these vacuum forces. Some researchers even speculate it could help explain dark energy, the mysterious force accelerating the universe's expansion. If empty space crackles with this much energy, could it be driving galaxies apart? Others wonder if manipulating these quantum fluctuations might one day lead to warp drive-like technologies where we stretch space-time itself. But perhaps the most humbling lesson lies in how the Casimir effect bridges worlds. It's a rare phenomenon where quantum mechanics and relativity shake hands, offering clues to a deeper theory that could unite them. Every time those plates move, they're not just obeying quantum rules, they're whispering secrets about the hidden structure of everything. And that's the real magic. Even in the void, the universe never stops surprising us. Some particles play by rules so strange they rewrite physics textbooks behind our backs. Take neutrinos, ghostly particles so insubstantial they pass through a light year of lead without a single collision. For decades, scientists assumed these cosmic phantoms were massless, zipping through space untouched by anything. Then came the bombshell. Neutrinos switch identities mid-flight, morphing between three flavors: electron, muon, and tau, like a chameleon cycling through colors. This phenomenon, called neutrino oscillation, proved these shadow particles must have mass after all, upending the standard model of particle physics and hinting at hidden layers in space-time itself. The first clues emerged from the Sun in the 1960s. Researchers detecting solar neutrinos found only a third of the expected number. At first, they suspected faulty equipment, until they realized the missing neutrinos hadn't vanished. They'd simply changed costumes. Imagine mailing 100 red balloons to a friend, only for them to receive 30 red, 30 blue, and 40 green. That's what was happening underground in detectors like Japan's Super Kamiok, and a tank filled with 50,000 tons of ultra-pure water lined with sensitive light sensors. When neutrinos interacted with the water, their flavor shifts left telltale patterns in the flashes of Cherenkov radiation, the aquatic equivalent of a sonic boom for light. But here's the twist that bends minds. For neutrinos to oscillate, they can't all be massless. Einstein's relativity allows particles with zero mass to only travel at light speed, experiencing no time, meaning no opportunity to change. The fact neutrinos switch flavors proves they must be moving slightly slower than light, ticking through internal clocks that let them transform. The kicker: their masses are absurdly tiny. A neutrino might weigh less than 1/1,000,000th of an electron, yet that minuscule heft cracks open the door to new physics. Some theories suggest neutrinos might be Majorana particles, their own antimatter twins, or that their mass comes from interactions with undiscovered dimensions curled up in space-time's fabric. Now consider the cosmic implications. Neutrinos outnumber atoms in the universe by 1,000,000,000 to 1, formed in abundance during the Big Bang and still streaming from stars, supernova, and even Earth's radioactive core. Their collective gravity could influence how galaxies cluster, while their mass might explain why the universe has more matter than antimatter, a mystery called baryon asymmetry. Experiments like IceCube, with sensors buried deep in Antarctic ice, are now catching ultra-high-energy neutrinos from cataclysmic events billions of light years away. Each one is a messenger carrying encrypted notes about black hole jets, colliding neutron stars, or processes we've yet to imagine. The real magic lies in how neutrino oscillations connect scales. These particles flirt with quantum weirdness while also threading the cosmic web, linking particle physics to the universe's large-scale structure. future detectors could hunt for sterile neutrinos, hypothetical fourth flavors that might interact only via gravity, potentially bridging to dark matter. Others might catch neutrinos bending space-time as they pass, testing whether these ethereal particles warp reality differently than matter does. Every oscillation hides a clue, whispering that the universe's greatest secrets might be carried not in starlight but in shadows. Sometimes the universe's greatest clues come disguised as glitches. For over a decade, NASA pioneered 10 and 11 spacecraft, humanity's first emissaries to the outer solar system, behaved in a way that defied explanation. After slingshotting past Jupiter in the 1970s, these twin probes should have coasted toward interstellar space, their trajectories governed by Newton's and Einstein's well-tested laws. Yet by the 1980s, tracking data revealed something startling. Both pioneers were slowing down ever so slightly, as if an invisible hand were tugging them backward toward the sun. This tiny deviation, just 10 billionths of a meter per second squared, became known as the Pioneer Anomaly, a whisper from the cosmos that physics might be missing a page from its playbook. At first, scientists scrambled to reconcile the numbers. Could it be drag from interstellar dust, a flaw in how we model the solar system's gravity, or most tantalizing evidence of new physics, like modifications to Einstein's equations or unseen dark matter tugging at the probes? The anomaly grew into one of space exploration's most enduring puzzles, precisely because it was so minuscule yet so persistent. Imagine throwing a paper airplane and watching it curve imperceptibly midair, defying every known law of aerodynamics. That's how confounding Pioneer's drift felt to physicists. Then came the Eureka, a moment in 2011. A team analyzing decades of telemetry realized the answer wasn't in the stars but in the spacecraft themselves. Pioneer's radioactive power sources, plutonium-fueled heaters, had been emitting infrared radiation asymmetrically. Most of this thermal energy radiated forward, but a fraction leaked backward, acting like a faint photon thruster pushing against the probe's motion. The effect was tiny, but over years and billions of miles, it added up to the observed slowdown. Case closed, not quite. While thermal radiation explained most of the anomaly, some researchers still debate whether it accounts for every last nanometer of drift, leaving a sliver of mystery alive. What's remarkable about the Pioneer anomaly isn't just the solution, but how it reshaped science along the way. To crack the case, researchers had to account for forces engineers normally ignore: the pressure of sunlight on spacecraft, the recoil from radio signals beamed to Earth, even the minuscule gravitational pull of the Kuiper Belt's unseen objects. It forced a new level of precision in deep space navigation, lessons now baked into missions like New Horizons, and it proved that even boring data, the kind most teams might dismiss as noise, can hide revolutionary insights. Think about it. If not for that unexplained deceleration, we might never have scrutinized thermal radiation's subtle effects so closely. Future missions to Europa or Enceladus now account for similar forces, ensuring their ice-penetrating radars and sample collectors aren't nudged off course by their own warmth. The Pioneer's legacy isn't just in the photos they beamed back from Jupiter and Saturn, but in teaching us that the universe often speaks loudest in the quietest anomalies. So the next time a spacecraft's path wobbles inexplicably, remember, it might not be a glitch but a clue wrapped in cosmic static. Imagine firing a single particle toward two slits and watching it somehow pass through both at once, not by splitting apart, but by existing in multiple states simultaneously. This is the quantum enigma at the heart of the double-slit experiment, a paradox so baffling it's been called the central mystery of quantum mechanics. Now, scientists are preparing to take this century-old experiment where it's never gone before, into the weightless environment of the International Space Station. Why? Because gravity, the weakest of nature's fundamental forces, yet the one that shapes galaxies, might be the missing piece in understanding why quantum particles behave so strangely. Here's the puzzle in a nutshell. When you send electrons or photons through two closely spaced slits, they don't behave like tiny bullets choosing one path. Instead, they act as waves, creating an interference pattern of light and dark bands on the detector behind the slits, as if each particle traveled through both openings simultaneously. But the moment you try to observe which slit the particle actually passes through, the interference vanishes. The particle chooses a single path, as if embarrassed to be caught in its quantum multitasking. This wave-particle duality has haunted physics since the 1920s, but one question remains unanswered. Does gravity play a role in this quantum dance? That's where the space station comes in. On Earth, even the most isolated lab can't fully escape gravity's whisper. It tugs at every atom, potentially introducing vibrations or decoherence, the process that makes quantum systems collapse into definite states. But in orbit, where objects are in perpetual free fall, researchers can create conditions 1,000,000 times quieter than any Earth-based experiment. The cold atom lab aboard the ISS already chills atoms to within a fraction of absolute zero, creating Bose-Einstein condensates, a state of matter where quantum effects become visible to the naked eye. Soon, it could host a zero-gravity version of the double-slit experiment, teasing apart whether gravity influences how and when quantum superposition unravels. Some theories suggest gravity might be the hidden actor behind quantum collapse. Roger Penrose's controversial gravitational or hypothesis proposes that when a quantum system becomes too massive, its own space-time curvature forces it to pick a single state. If true, this would mean the universe has been running two rulebooks all along: quantum mechanics for the small, general relativity for the large, with gravity quietly translating between them. A space-based double-slit experiment could test this by varying the mass of the particles used. If heavier particles like large molecules show different interference patterns than lighter ones in 0G, it might hint at gravity's subtle hand in shaping quantum reality. But the implications reach even further. Quantum systems are famously fragile, yet life, and indeed the universe, relies on their stability. Photosynthesis, bird migration, even the fusion engines of stars all exploit quantum coherence. If gravity disrupts these processes, understanding how could revolutionize everything from quantum computing to our models of the early cosmos. Picture a quantum computer on Earth struggling to maintain coherence, while its orbital counterpart hums along flawlessly, shielded from gravitational noise. Or consider the birth of the universe. When quantum fluctuations ballooned into galactic structures, did space-time's curvature guide that transformation? What makes this experiment so thrilling isn't just the potential answers, but the audacity of the question itself. For decades, we've treated quantum mechanics and gravity as separate domains, their contradictions swept under the rug. Now, by sending a quantum paradox into orbit, we're not just testing a theory, we're probing the seams of reality, asking whether the universe's two greatest frameworks might finally shake hands. And if they do, the view from that handshake could change everything. Buried in the static of empty space lies the oldest photograph ever taken, a grainy snapshot of the universe at just 380,000 years old. This is the cosmic microwave background, or CMB, the cooled remnants of the Big Bang's searing flash stretched into faint microwaves over 13.8 billion years. But don't let its uniform appearance fool you. Those barely perceptible temperature variations, fluctuations as tiny as 1 part in 100,000, are actually space-time's baby pictures, capturing density ripples that would later grow into galaxies, clusters, and the vast cosmic web we see today. The story of how we decoded this primordial light reads like a scientific thriller. In 1965, Bell Labs engineers Arno Penzias and Robert Wilson stumbled upon persistent microwave noise coming from every direction in space, an annoyance they initially blamed on pigeon droppings in their antenna. After scrubbing the equipment clean and still finding the signal, they realized they'd detected the CMB, earning them a Nobel Prize and confirming the Big Bang Theory. But the real breakthrough came in 1992 when NASA COBE satellite unveiled the CMB's hidden texture, those microscopic hot and cold spots, some just slightly warmer than others, weren't random noise. They were quantum fluctuations from the universe's first trillionth of a second, magnified by cosmic inflation into the seeds of all structure. Here's why these ancient wrinkles matter. The pattern of warmer and cooler regions encodes astonishing details about space-time's geometry. Imagine throwing a pebble into a pond. The ripples spread in predictable ways depending on whether the pond is flat, spherical, or curved like a saddle. The CMB works the same way. By measuring how those temperature variations correlate across different angular scales, cosmologists can deduce the universe's shape. The stunning conclusion: space-time appears remarkably flat on large scales, a finding that bolsters inflation theory's prediction of exponential expansion smoothing out any primordial curvature. But the CMB isn't just about geometry. Its polarization, the slight directional preference of those microwaves, carries even deeper clues. Some photons scattered off electrons in the early universe, imprinting a swirling pattern called B-mode polarization that could reveal gravitational waves from inflation itself. In 2014, the BICEP 2 team thought they'd spotted this smoking gun in data from Antarctica, only to learn cosmic dust had muddled the signal. Yet the hunt continues, with next-generation telescopes like the Simons Observatory and Lightbird poised to separate inflationary whispers from interstellar noise. What's truly humbling is how much remains hidden in this afterglow. The CMB's finest details might contain evidence of parallel universes, extra dimensions, or even the universe's ultimate fate. Some models suggest certain patterns could indicate whether space-time is fundamentally discrete, pixelated at the Planck scale, or if dark energy's grip will eventually tear reality apart. Every new CMB map is like peeling another layer off an onion, revealing questions we didn't even know to ask. And all of it stems from that faint microwave hiss, a relic so cold it's just 2.7 degrees above absolute zero, yet burning with secrets about existence itself. Gravity plays no favorites whether it's a feather or a cannonball. All objects in a vacuum fall at the same rate. This simple truth, demonstrated by Galileo's legendary, if apocryphal Leaning Tower of Pisa experiment, hides a profound secret about the universe. But it wasn't until the late 19th century that Hungarian physicist Laurent Ertvers devised a way to test this principle with jaw-dropping precision. His experiment didn't just confirm that gravity treats all masses equally, it revealed why, exposing a fundamental link between acceleration and gravity that would later become the foundation of Einstein's general relativity. Ertvers's apparatus was deceptively elegant, a torsion balance, essentially a horizontal bar suspended by a thin wire with two different masses attached at each end. If gravity pulled on these masses differently, say, because their composition affected how they responded to Earth's gravitational field, the imbalance would cause the wire to twist ever so slightly. But after years of meticulous measurements, Ertvers found no twist. Whether the weights were made of gold, platinum, or even antimony, gravity treated them identically, down to 1 part in a billion. This wasn't just a victory for experimental precision. It was the first hard evidence that gravitational mass, how hard gravity pulls an object, and inertial mass, how much an object resists acceleration, are one and the same. Einstein would later elevate this observation into his equivalence principle, the idea that standing in a gravitational field is indistinguishable from being in an accelerating spaceship. Picture yourself in a windowless elevator. If the cable snaps and you begin free falling, you'd float weightlessly, unable to tell whether gravity has vanished or the elevator is simply accelerating downward at 9.8 meters per second squared. Conversely, if the elevator were magically pulled upward at that same rate, you'd feel your feet planted firmly on the floor, just as if you were standing on Earth. This symmetry isn't just a clever thought experiment, it's the reason space-time must curve. Here's the kicker: if all objects follow the same paths in a gravitational field, then gravity isn't really a force at all, it's the shape of space-time itself. Imagine rolling marbles across a trampoline. Place a bowling ball in the center, and the marbles will curve inward, not because some invisible hand pushes them, but because the trampoline's surface is warped. Ertvers' experiment hinted at this reality, proving that the stage of the universe isn't flat and passive, but dynamic and responsive. Modern versions of the Ertvers experiment have pushed the limits even further. Satellite missions like Microscope, launched in 2016, have tested the equivalence principle in orbit, where Earth's gravity is weaker, but measurements can be thousands of times more sensitive. The results: still no violation, even at precisions of 1 part in a quadrillion. But physicists keep looking because any tiny discrepancy could crack open the door to new physics, perhaps a sign of extra dimensions or a bridge between quantum mechanics and gravity. What's truly remarkable is how a 19th century experiment with hanging weights became a cornerstone of our deepest cosmic theories. Ertvers couldn't have known his work would help explain black holes or the Big Bang, but his obsession with precision revealed a truth woven into the fabric of reality. Gravity doesn't discriminate because at its core, it's not pulling us downward, it's inviting us to follow the curves of space-time itself. What if you could watch time itself stretch and bend? In 1964, physicist Erwin Shapiro proposed a radical test of Einstein's relativity that sounded like science fiction. Send radar signals past the sun and measure how long they take to bounce back. Common sense says light travels at a constant speed, but Shapiro suspected the sun's gravity would act like cosmic molasses, slowing the signals ever so slightly as they grazed warped space-time. When his team at MIT finally performed the experiment in 1966 using Venus as a mirror, the results were unmistakable. The radar echoes returning near the sun's edge arrived 200 microseconds later than those traveling farther out. That delay, now called the Shapiro time delay, wasn't just proof of relativity in action. It revealed that even light, the universe's speedster, can't escape gravity's grip on reality's fabric. Here's what makes this phenomenon so strange. Light always moves at the same speed in a vacuum, that's relativity's golden rule. But near a massive object, space-time curves so drastically that the light isn't actually slowing down. It's taking a longer path through distorted geometry. Picture two hikers crossing a mountain. One goes around the base while the other scales the peak. Though both walk at the same speed, the climber covers more ground due to the terrain's shape. Similarly, light skimming the sun traverses more space-time elevation, creating the illusion of delay. This subtle effect, measurable only with precise atomic clocks and planetary alignments, became the ultimate stress test for Einstein's equations. Fast forward to today, and the Shapiro delay isn't just a textbook curiosity, it's a tool reshaping astronomy. By analyzing how radio signals from spacecraft like Cassini or Mars orbiters slow when passing behind the Sun, scientists have mapped the solar corona's turbulent plasma with unprecedented detail. But the real magic happens beyond our solar system. When distant exoplanets transit their stars, their gravity creates miniature Shapiro delays in the star's light, allowing astronomers to weigh worlds light years away. In 2016, this technique helped confirm Proxima Centauri b, an Earth-sized exoplanet in the closest star system to us, by detecting its gravitational fingerprint in starlight. The most mind-bending application, probing dark matter's invisible grip, some galaxies exhibit Shapiro delays far greater than their visible mass should cause, hinting at vast halos of unseen matter warping space-time around them. Others show anomalies that could point to modifications of gravity itself, clues that Einstein's theory, for all its brilliance, might need tweaking at cosmic scales. Future missions like the European Space Agency's Ariel telescope will harness Shapiro delays to study exoplanet atmospheres, while pulsar timing arrays use the effect to hunt for gravitational waves from supermassive black hole mergers. What began as a clever test of relativity has become a universal measuring stick, revealing hidden layers of reality from our cosmic backyard to the edge of the observable universe. And the most humbling lesson, that a 200 microsecond delay, barely the blink of a fruit fly's wing, could unlock secrets spanning from the Sun's fiery corona to the dark matter scaffolding of the cosmos. Think of Earth not just as a planet, but as a spoon swirling through the universe's thickest honey. As it rotates, it doesn't just move through space, it twists the fabric of space-time around it, dragging the very stage of reality along for the ride. This bizarre phenomenon, called the lens-thirring effect or frame dragging, was one of Einstein's wildest predictions. Massive rotating objects don't just bend space-time, they pull it into a swirling vortex around them. For decades, it remained a mathematical curiosity, seemingly impossible to measure. Then, in 2004, NASA, a Gravity Probe B mission, did the unthinkable. It caught Earth red-handed, warping space-time with every turn. The numbers behind this effect are staggering. Earth's rotation drags space-time around it at a rate of about 39 milliarcseconds per year, roughly the angle a snowflake makes when viewed from a mile away. Detecting this required gyroscopes so precise they could spot a human hair's width from 10 miles distant. Gravity Probe B's spinning spheres, kept in near-perfect isolation, gradually tilted as they orbited, their axes tracing the invisible whirlpool of space-time around our planet. The results matched Einstein's equations to within 1%, proving that rotation isn't just a property of objects, it's a sculptor of reality itself. But here's where it gets cosmic. The lens-thirring effect isn't just a quirk of Earth, it's universal. Neutron stars, spinning hundreds of times per second, drag space-time so violently they fling near-by matter into dizzying spirals. Supermassive black holes, like the one at our galaxy's center, twist space-time into knots so tight they could theoretically serve as time machines, looping trajectories into closed time-like curves. Even the entire universe might exhibit frame dragging on a grand scale, with the collective rotation of galaxies potentially imprinting a faint swirl on the cosmic microwave background. What's truly revolutionary is how this effect bridges scales. The same phenomenon that tilts a satellite's gyroscope also shapes the jets of quasars, those brilliant beams of energy shooting from active galaxies. Frame dragging near black holes might explain why some particle streams reach near light speeds, as if space-time itself is a cosmic conveyor belt. Future missions like LISA, a space-based gravitational wave detector, could hunt for these twists in the mergers of spinning black holes, where space-time becomes a spinning top wobbling under extreme forces. The lesson hidden in these subtle tilts, motion and gravity, are two sides of the same coin. A spinning planet isn't just an object in space, it's an artist, etching its rotation into the universe's canvas. And as we learn to read those brushstrokes, we're uncovering a truth far stranger than fiction. The cosmos doesn't just have a stage, it's dancing on it. Science thrives on surprises, but few caused as much uproar as the day neutrinos appeared to break the universe's speed limit. In 2011, the Opera experiment in Italy made headlines worldwide with an impossible claim. Subatomic particles called neutrinos had traveled from CERN in Switzerland to Gran Sasso, 730 kilometers away, 60 nanoseconds faster than light should have managed. If true, this shattered Einstein's century-old axiom that nothing outpaces light speed. The implications were staggering: time travel, causality violations, a complete rewrite of physics. Then came the twist no one expected. The result was wrong. A loose fiber optic cable and an improperly synced clock had skewed the measurements. Yet this failure became one of modern science's most profound lessons in humility and rigor. The Opera team's original findings weren't reckless, they were meticulous. Over 3 years, they'd fired 15,000 neutrino beams through Earth's crust, timing their journey to within billionths of a second. When the data consistently showed neutrinos arriving early, they triple-checked everything before publishing, openly inviting scrutiny. That transparency proved crucial. Independent teams quickly identified two tiny but critical flaws: a GPS receiver's faulty connection that underestimated the neutrino's flight time, and an oscillator ticking slightly off rhythm. Once fixed, the anomaly vanished. The neutrinos, it turned out, were obeying relativity after all. What makes this episode extraordinary isn't the mistake, it's how science responded. Rather than clinging to a sensational result, the Opera collaboration publicly retracted their claim within months, reaffirming a core principle: evidence trumps ego. This self-correcting mechanism is science's superpower. For every headline-grabbing discovery, there are countless quiet corrections ensuring only robust truths endure. The Opera incident became a masterclass in peer review's importance, showing how collective skepticism sharpens our understanding of reality's rules. But the story doesn't end there. While neutrinos didn't break light speed, their near-light velocity reveals deeper mysteries. These particles flirt with the universe's ultimate pace limit, their behavior exposing gaps in the standard model. Opera precision measurements later helped confirm neutrino oscillations, proving these phantoms have mass, a finding that clinched the 2015 Nobel Prize. The experiment's original goal, studying how neutrinos change flavors, succeeded spectacularly, even as its accidental detour into speed testing became a cautionary tale. Perhaps the most enduring lesson lies in how Opera refined our approach to space-time's edge cases. Future experiments now account for picosecond timing errors and thermal effects on cables, while neutrino detectors like Japan's hyper-Kamiok and apply even stricter verification. The episode also sparked new discussions. Could certain quantum phenomena appear to outpace light without violating relativity? Are there space-time geometries where neutrinos take unexpected shortcuts? By probing these questions, we're not just testing Einstein, we're stress-testing the scientific method itself. In the end, Opera ghostly speedsters taught us that even wrong answers propel discovery. The pursuit of those 60 nanoseconds didn't undermine relativity, it reinforced it, while reminding us that the cosmos guards its secrets well. Every anomaly, whether confirmed or corrected, is a stepping stone toward truths we've yet to imagine. In the early 20th century, as Einstein's equations were reshaping our understanding of gravity, a handful of mathematicians peered deeper into the numbers and glimpsed something astonishing: the universe wasn't static. It was stretching. The Friedmann-Lemaitre-Albertson-Walker metric, a mouthful of names that barely fits on a textbook page, became the Rosetta Stone for decoding cosmic expansion. At its heart lies a deceptively simple idea. Space-time isn't just curved by mass. Its very fabric evolves, carrying galaxies along like raisins in rising bread dough. The story begins with Alexander Friedmann, a Russian meteorologist turned cosmologist who, in 1922, solved Einstein's equations for a dynamic universe, only to have Einstein initially dismiss the result as a mathematical curiosity. Then came Georges Lemaitre, a Belgian priest-physicist who not only derived the same solution independently but went further, proposing that an expanding universe implied a fiery beginning. His primeval atom theory, later dubbed the Big Bang, was met with skepticism until Edwin Hubble's observations of receding galaxies proved space itself was stretching. By the 1930s, American Howard Robertson and British mathematician Arthur Walker had refined the framework, giving us the FLRW metric we use today, a mathematical compass for navigating cosmic history. What makes this metric so revolutionary is how it connects the dots between geometry and destiny. The equations describe space-time's curvature on cosmic scales, revealing three possible fates: a universe that expands forever open, collapses back on itself closed, or balances on a knife's edge flat. Each scenario depends on the density of matter and energy, a relationship that later led to the shocking discovery of dark energy. When astronomers found the universe's expansion wasn't slowing down as expected but accelerating, the FLRW metric was the lens that made sense of it. Suddenly, those abstract symbols in Friedmann's notebooks were describing a cosmos dominated by an invisible force pushing galaxies apart. But here's where it gets even wilder. The FLRW metric doesn't just describe expansion, it lets us rewind the cosmic film. By plugging in today's observed rates, we can trace the universe backward to a hot, dense singularity, confirming Lemaitre's once controversial Big Bang. It also predicts subtle fingerprints in the cosmic microwave background, patterns that satellites like Planck have since measured with exquisite precision. Those faint temperature variations, they're the universe's baby pictures, encoded with details about space-time's shape and composition. Yet the metric's greatest gift might be its unfinished questions. Why does the universe appear so finely balanced between expansion and collapse? What exactly is dark energy, and could its strength change over time? The FLRW framework doesn't answer these puzzles, it frames them, offering a language to test bold new ideas. Some theorists tweak its equations to explore cyclic universes or higher dimensions, while others use it to hunt for deviations that might reveal quantum gravity's fingerprints. The beauty of this mathematical tool lies in its humility. It doesn't pretend to explain everything, just to map the relationship between space-time's curvature and the matter within it. And in that mapping, we've uncovered a cosmos far stranger than Friedmann or Lemaitre ever imagined, one where empty space pulses with dark energy, where the past flickers in microwave static, and where the future hinges on equations scribbled decades before telescopes could test them. The universe, it turns out, speaks in geometry, and thanks to these pioneers, we're finally learning to listen. Imagine holding a map so vast it charts over 1 million galaxies, each one a glowing pinprick in the dark, a cosmic atlas revealing not just where these islands of stars lie, but the hidden architecture connecting them all. This is the Sloan Digital Sky Survey, one of the most ambitious cartography projects in history, turning Earth into a lens through which we've glimpsed the universe's skeletal structure. What began in 1998 as a humble telescope in New Mexico has since rewritten our understanding of space-time's grand design, exposing a web of galaxies strung along filaments of dark matter, a pattern so colossal it makes even the largest superclusters look like threads in a tapestry. The survey's magic lies in its method. Using a specially designed 2.5-meter telescope equipped with a 500-megapixel camera, astronomers didn't just photograph galaxies, they dissected their light. Every spectrum captured revealed a galaxy's composition, distance, and velocity, allowing scientists to reconstruct their three-dimensional positions across billions of light years. Like listening to an orchestra where each instrument's pitch betrays its location, the team translated redshift, the stretching of light as galaxies race away from us, into a roadmap of the cosmos. The result, a revelation that galaxies aren't scattered randomly but cling to vast, crisscrossing tendrils, with yawning voids between them so empty they could swallow thousands of Milky Ways whole. But here's where space-time's fingerprints emerge. Those galactic filaments trace the valleys of an invisible topography, shaped by dark matter's gravitational pull and space-time's curvature. Picture rolling a handful of marbles onto a stretched bed sheet. They'll naturally roll into the dips created by hidden weights beneath the fabric. The Sloan survey showed our universe works the same way, with galaxies sliding into the gravitational wells carved by dark matter's unseen mass. Some filaments stretch over 500 million light-years, their curvature so slight it's only visible when you step back and see the pattern across millions of data points. The survey's most startling contribution might be how it exposed dark energy's handiwork. By measuring how the cosmic web structure has evolved over time, astronomers noticed something peculiar. The universe's expansion isn't just continuing, it's accelerating, as if some repulsive force is stretching the very grid on which galaxies are pinned. This discovery, which earned the 2011 Nobel Prize in Physics, hinged on the Sloan data's precision, proving that space-time isn't just curved by matter. It's being stretched by an enigmatic energy woven into its fabric. Now zoom in on one of those filaments and you'll find another surprise. The galaxies within them aren't motionless. They're streaming along these invisible highways, pulled by gravity toward dense knots where filaments intersect. These nodes, rich with clusters of galaxies, act like cosmic metropolises, drawing in smaller towns along dark matter's intergalactic freeways. The Sloan team even spotted our own Milky Way caught in this flow, part of a slow-motion migration toward the Shapley supercluster, a gravitational megalopolis 650 million light-years away. What began as a mapping project has become a time machine. By comparing the survey's modern snapshots with simulations of the early universe, scientists can now trace how tiny quantum fluctuations from the Big Bang ballooned into the web we see today. Future expansions of the survey, like the Dark Energy Spectroscopic Instrument, will probe even deeper, hunting for distortions in the web's pattern that might reveal secrets about neutrinos or the universe's very first seconds. The true legacy of the Sloan Digital Sky Survey isn't just in the data, it's in how it reshaped our cosmic perspective. Those glowing dots on the map aren't isolated islands, they're traces of a hidden lattice, the scaffolding upon which space-time has stretched and curved over billions of years. And somewhere in that labyrinth of light and shadow, the next great mystery of gravity is waiting to be found. The quantum eraser experiment doesn't just bend the rules, it rewrites them mid-game. Picture firing photons one by one through a double-slit apparatus, where they create the familiar interference pattern of waves. Now add a twist, detectors at the slits to record which path each photon takes. Instantly, the interference vanishes as if the particles, now aware they're being watched, abandon their wave-like behavior. But what if you erase that path information after the photons have already hit the detector? Astonishingly, the interference pattern reappears, as though the photons return their past to behave as if they were never observed. This isn't just quantum weirdness, it's a direct challenge to our understanding of cause and effect, suggesting that particles might choose their history retroactively, long after the experiment seems over. Delayed choice variations of this experiment push the paradox even further. In one setup, scientists decide whether to measure a photon's path after it's already passed through the slits, yet the photon's behavior changes as if it anticipates the future decision. It's as if flipping a coin today could alter whether it landed heads or tails yesterday. These results don't just blur the line between past and present, they dissolve it entirely, hinting that space-time's arrow might be more like a suggestion than a law. Some interpretations propose that quantum systems exist in a superposition of all possible histories until a measurement locks one into place, effectively rewriting the past to fit the observed present. The implications ripple far beyond the lab. If quantum events lack a fixed timeline, could the universe itself be a tapestry of flexible causality? Cosmologists like John Wheeler speculated that observations made now might influence events near the Big Bang, a cosmic-scale version of the delayed choice experiment. Even black holes, those ultimate disruptors of space-time, might host similar paradoxes at their event horizons, wherein falling matter's fate hinges on distant future observations. Yet the real magic lies in how these experiments reframe reality's scaffolding. Space-time, long seen as an immutable stage, might instead be a dynamic script, editable until the last act. Future quantum networks or gravity wave detectors could test whether this retrocausality persists across macroscopic scales, probing if the universe truly keeps its options open until the final moment. Until then, the quantum eraser stands as a humbling reminder. The universe's clock may not tick in just one direction. What if faster-than-light travel wasn't about moving through space, but bending space itself around you? In 1994, Mexican physicist Miguel Alcubierre proposed an idea straight out of science fiction, a warp drive that wouldn't propel a ship through the cosmos, but would instead manipulate space-time to bring the cosmos to the ship. The concept hinges on one of general relativity's most startling loopholes. While nothing can travel through space faster than light, space itself can expand or contract at any speed. Picture standing on a moving walkway at the airport. Your feet aren't moving faster, but the ground beneath you is, carrying you forward effortlessly. Alcubierre's warp drive applies this principle to the fabric of reality, compressing space-time in front of a spacecraft while expanding it behind, creating a wave that carries the vessel at velocities that could dwarf light speed without ever locally violating Einstein's speed limit. The mathematics behind this idea is deceptively elegant. Alcubierre's solution to Einstein's equations describes a bubble of flat space-time enveloping the ship, surrounded by a warped region where space contracts ahead and stretches behind. Inside this bubble, passengers would experience no acceleration forces, no crushing g-forces, no time dilation extremes, just the eerie sight of stars ahead bunching together like cars in traffic, while those behind stretch into red-shifted oblivion. The effect resembles surfing a cosmic tsunami, where the wave's motion does the work while the surfer remains stationary relative to the water. But here's the catch that keeps warp drives in the realm of theory. Creating such a bubble requires exotic matter with negative energy density, a substance that defies everyday physics by possessing negative mass. Think of it as anti-gravity glue, capable of propping open the expanded space behind the bubble while pinching shut the space ahead. While quantum mechanics allows for fleeting instances of negative energy like the Casimir effect between plates, Scaling this up to warp drive proportions would demand energies comparable to annihilating Jupiter's mass, plus control over phenomena we've barely begun to understand. Recent breakthroughs, however, have softened the impossible into the merely improbable. NASA Eagleworks Lab has explored microscopic warp field interferometry, hunting for space-time distortions in lab-scale experiments. Theoretical refinements suggest ways to reduce the energy requirements from planetary scales to something closer to a few tons of matter, still monumental but no longer laughable. Some models even propose harnessing dark energy, the same mysterious force accelerating the universe's expansion, as a potential power source. The real magic of Alcubierre's idea isn't just the engineering challenge, it's how it reframes our cosmic ambitions. If humanity ever constructs a warp drive, it won't be through brute force rocketry, but by mastering space-time's geometry like a sculptor molds clay. Imagine reaching Alpha Centauri not by spending decades in transit, but by folding the distance until it's a day's journey. Or consider the philosophical implications. A civilization with such technology wouldn't just explore the universe, it would reshape the very concept of distance. Of course, unanswered questions loom like event horizons. Would a warp bubble accumulate lethal cosmic rays at its leading edge? Could it destabilize and vaporize a solar system upon arrival? The math remains silent on these practicalities for now. But the mere fact that warp drives aren't forbidden by relativity is a revelation. They remind us that the universe's rulebook is stranger than we dreamed, and that the line between impossible and inevitable often depends on who's reading the equations. The holometer at Fermilab isn't just another physics experiment, it's a reality check in the most literal sense. This unassuming array of lasers and mirrors is hunting for something far stranger than dark matter or exotic particles. It's searching for proof that the universe itself might be pixelated. Imagine zooming in on a digital photo until you see the individual squares that compose it. The holometer is trying to do just that with space-time, probing whether what we perceive as smooth, continuous reality might actually be built from tiny, discrete chunks at the Planck scale, units so small that 1,000,000 billion of them could fit across a single proton. At its core, the experiment tests a radical idea inspired by black hole physics. That information in the universe might follow holographic principles, with all three-dimensional reality encoded on a two-dimensional surface at the quantum level. If true, this would mean space-time has a fundamental resolution limit, like the refresh rate on a cosmic monitor. The holometer's approach is ingeniously simple. It splits a laser beam down two perpendicular 40-meter-long vacuum tubes, then recombines them to look for microscopic jitter in the light waves. Why? Because if space-time is pixelated, those Planck-scale fluctuations should introduce a subtle noise, a kind of quantum static, as the laser's path stutters across the grid-like structure of reality itself. What's mind-bending isn't just the scale of this hunt, but the implications. If the holometer detects this holographic noise, it would mean that space-time isn't the smooth fabric Einstein described, but more like a cosmic digital display with every event in the universe, from a supernova explosion to your morning coffee, rendered on an invisible quantum pixel grid. Some theories suggest this could resolve the long-standing conflict between general relativity and quantum mechanics, providing a natural cutoff point where gravity's smooth curves meet the grainy uncertainty of the quantum world. Yet even a null result would be revolutionary. If the holometer finds no evidence of pixelation, it forces physicists to reconsider alternative explanations for how information scales in the universe, perhaps pointing toward emergent space-time theories where dimensionality itself isn't fundamental, but arises from deeper, more abstract quantum relationships. The experiment's sensitivity is staggering. It can detect movements smaller than a thousandth of a proton's width, making it effectively a microscope for the fabric of reality. What makes this quest so compelling is how it bridges philosophy and hard science. For centuries, thinkers have pondered whether reality is continuous or discrete, an ancient debate now being tested with laser precision. If the universe does operate with Planck-scale pixels, it might explain why we hit computational walls when simulating quantum gravity, or why black holes seem to have maximum entropy limits. Future upgrades or successors to the holometer could push the search even deeper, potentially revealing whether space-time structure changes near massive objects or at cosmic horizons. For now, the holometer stands as one of the most audacious experiments ever conceived, not just studying the universe, but interrogating its very architecture. Whether it finds noise or silence, the answer will rewrite our understanding of existence, proving once again that the deepest truths often lie not in the stars, but in the spaces between them. Deep beneath the border of France and Switzerland, in a tunnel wide enough to drive a truck through, scientists are recreating the universe's first moments not with telescopes, but by smashing atomic nuclei together at nearly the speed of light. The Large Hadron Collider's heavy ion collisions don't just produce new particles, they melt the very fabric of matter itself, forging a primordial soup called quark-gluon plasma. This isn't just any exotic substance, it's the closest thing we've ever made to the newborn universe, a state of matter so extreme it flows with perfect, frictionless precision, defying everything we know about viscosity. Here's the astonishing part. When gold or lead nuclei collide head-on in the LHC's 17-mile ring, their protons and neutrons briefly dissolve into their fundamental ingredients, quarks and gluons. For a sliver of time shorter than a millionth of a billionth of a second, these particles forget their usual rules, behaving not like individual actors but as a single, ultra-hot liquid. The temperatures inside this fireball reach over 5 trillion degrees, 350,000 times hotter than the sun's core matching conditions last seen a microsecond after the Big Bang. What emerges isn't chaos, but something eerily harmonious. This quark-gluon plasma doesn't ooze like honey or splash like water. It flows with near-zero resistance, making even the smoothest superfluid look clumsy by comparison. But why does this matter? Because this plasma isn't just a curiosity. It's a window into how space-time itself might have behaved in the universe's infancy. At these energies, the distinction between matter and the fabric of reality blurs. Some theories suggest that in these extreme states, space-time could have exhibited fluid-like properties, rippling and swirling in ways that later froze into the more rigid geometry we know today. The LHC's detectors, like ALICE, are essentially cosmic time machines, capturing how these primordial droplets expand and cool, mimicking the universe's own expansion in ultra-fast motion. The data holds surprises. Instead of the expected gaseous behavior, the plasma behaves like a nearly perfect liquid, with viscosity so low it approaches a theoretical limit set by quantum mechanics. This discovery forced physicists to rethink how matter behaves under such extreme densities, and by extension, how the early universe might have transitioned from this soupy state to the structured cosmos we see today. Some researchers even speculate that similar conditions might exist in neutron star mergers, where gravitational waves and quark-gluon signatures could overlap, offering a new way to study these exotic states through multi-messenger astronomy. What's truly revolutionary is how these experiments bridge scales. The same physics that governs a trillion-degree quark soup might also explain why black holes have entropy or how information scrambles in quantum systems. Future upgrades to the LHC and next-generation colliders could push these recreations even closer to the Big Bang's first instance, potentially revealing phase transitions where space-time itself crystallized into its current form. For now, each heavy ion collision is like replaying the universe's first notes, listening for harmonics we've yet to understand. And in that fleeting fireball, we're not just observing the past, we're touching it. Floating 250 miles above Earth, the Alpha Magnetic Spectrometer isn't just another space station experiment, it's a cosmic eavesdropper, tuned to the universe's most energetic whispers. Since its installation on the International Space Station in 2011, AMS-02 has been sifting through billions of cosmic rays, hunting for anomalies that could rewrite our understanding of reality. These aren't just random particles, they're celestial messengers, some hurled across galaxies by supernova explosions or spinning neutron stars, others possibly forged in collisions between invisible dark matter. Each one carries a story, and the spectrometer reads them all with precision down to 1 part in 10 billion, the equivalent of spotting a single misaligned grain of sand on an entire beach. What makes AMS-02 revolutionary isn't just its sensitivity, but its ability to distinguish matter from antimatter in these high-energy projectiles. At its core lies a powerful magnet that bends incoming particles' paths, allowing detectors to identify their charge and mass. This is crucial because antimatter cosmic rays like positrons or antiprotons are extraordinarily rare, and their unexpected abundance could signal exotic processes. In 2013, the experiment sparked global excitement when it detected more high-energy positrons than standard astrophysics could explain, one tantalizing possibility. These excess particles might be the fingerprints of dark matter annihilations, where hypothetical weakly interacting massive particles collide and decay into detectable fragments. But the plot thickens when you consider space-time's hidden architecture. Some theories suggest that certain cosmic ray anomalies could hint at extra dimensions curled up at microscopic scales. Imagine space isn't just the 3 dimensions we see, but has additional hidden directions like a garden hose that looks one-dimensional from afar but reveals its cylindrical surface up close. If cosmic rays interact with these unseen dimensions, their energy spectra might bear subtle distortions like echoes bouncing through unseen corridors. AMS-02 data could reveal these whispers, offering the first experimental clues to string theory's elusive predictions. The instrument's location on the ISS isn't just for show. Unlike ground-based detectors, which see only the debris of cosmic rays that survive atmospheric collisions, AMS-02 catches these particles pristine before Earth's air scrambles their signatures. Over a decade of operation, it's logged over 200 billion cosmic ray events, creating a map of the universe's particle traffic so detailed it's like comparing a medieval star chart to a modern GPS. Recent findings show unexpected patterns in the ratios of helium to proton, fluxes at certain energies, another puzzle that might point to undiscovered physics. What's often overlooked is how this experiment bridges scales. The same cosmic rays AMS-02 studies shape space-time's ecology, from seeding lightning storms in Jupiter's atmosphere to potentially influencing mutation rates in DNA. Future upgrades or successor missions could focus on ultra-heavy cosmic rays, nuclei like iron or even uranium, accelerated to near light speed, whose trajectories might betray distortions caused by warped space-time near distant black holes. Every anomaly, every statistical bump in the data isn't just a curiosity. It's a potential thread in the tapestry of a grander theory waiting to be woven. As AMS-02 enters its second decade, its greatest legacy might be the questions no one thought to ask, whether it's dark matter's shadow, extra dimensions' fingerprints, or something entirely unforeseen. This unassuming module on the ISS proves that sometimes the universe's deepest secrets arrive not with a bang, but in the silent rain of particles from the void. Launched in 2013, the European Space Agency's Gaia spacecraft doesn't just observe stars, it listens to the silent symphony of gravity's influence across the Milky Way. Orbiting at a stable point 1.5 million kilometers from Earth, this unassuming observatory has spent nearly a decade performing the most precise stellar census in history, tracking the positions, movements, and even color shifts of over 1 billion stars with accuracy so sharp it could spot a human hair on the Moon from Earth. But Gaia's true revolution lies in what these star trails reveal: the invisible scaffolding of dark matter warping space-time across our galaxy, written in the subtle deflections of starlight we've overlooked for centuries. Imagine the Milky Way not as a flat disk of stars, but as a vast trampoline sagging under unseen weights. Each star's path isn't just governed by the visible objects around it, it's tugged by the gravity of hidden mass bending the space it travels through. Gaia detects these distortions by measuring proper motion, the tiny, real space movements of stars across the sky, and radial velocity. There, toward or away, motions glean from starlight's redshift or blueshift. Combined, these vectors create a three-dimensional velocity map so detailed it exposes where stars deviate from expected orbits, betraying the hand of dark matter's invisible grip. The spacecraft's third data release in 2022 delivered bombshell revelations. By analyzing the wobbles of 12,000 hypervelocity stars, celestial speedsters racing fast enough to escape the galaxy, Gaia traced tendrils of dark matter, flinging them outward like slingshots. Other anomalies emerged too, entire star streams bending as if around unseen obstacles, and ghostly ripples in the galactic disk suggesting past collisions with dwarf galaxies whose dark matter halos left gravitational scars. Most startling were the galactic wobbles, subtle shifts in the Milky Way's outer rotation curve that shouldn't exist unless our galaxy is embedded in a vast, asymmetric cloud of dark matter, far larger than its visible stars and gas. What makes Gaia's mission unique is how it turns stars into gravity sensors. Unlike telescopes that hunt for dark matter directly, Gaia exploits relativity's core premise, that mass tells space-time how to curve, and space-time tells mass how to move. Each star's aberrant path becomes a probe into the warped geometry around it, like watching leaves caught in invisible whirlpools. This approach has already uncovered phantom galaxies, dark matter clumps with almost no stars whose existence was previously only theoretical. One such structure, nicknamed Nix, may be the remnant of a long-ago galactic merger, now detectable only through its gravitational fingerprint on stellar motions. The implications stretch far beyond mapping. Gaia's data suggests dark matter isn't smoothly distributed, but clumped in ways that challenge standard models. Some regions show stars moving as if space-time itself has fine wrinkles, microscopic curvature variations that could hint at dark matter's quantum nature. Other areas reveal unexpected symmetries, as if the galaxy's hidden skeleton follows geometric rules we've yet to decipher. Future data releases will sharpen this map further, potentially unveiling actions or other hypothetical particles through their subtle gravitational whispers. Yet Gaia's greatest gift might be temporal. By comparing stellar motions today with historical records like the Hipparcos catalogue, astronomers can rewind the galaxy's evolution, watching how dark matter's gravitational wells guided stars over millennia. It's like finding an ancient ship's log where every entry was written in gravity's hand. And as Gaia continues its scan, each new data point adds another stitch to the tapestry, a living portrait of the universe's hidden architecture, painted not in light, but in the silent dance of warped space-time. High above the Arizona desert, 4 enormous mirrored dishes stare into the night sky, waiting for flashes of light so faint they might as well be cosmic fireflies. This is Veritas, the Very Energetic Radiation Imaging Telescope Array System, and it's hunting for gamma rays with energies millions of times greater than visible light. But here's the twist: these aren't just any gamma rays. They're celestial messengers that have traveled billions of light years, their paths subtly warped by the universe's hidden magnetic fields and the gravitational pull of invisible matter. Every time one of these high-energy photons slams into Earth's atmosphere, creating a cascade of secondary particles that Veritas detects, it carries encrypted notes about the large-scale structure of space-time itself. What makes this observatory extraordinary isn't just its sensitivity, it's how it turns gamma rays into cosmic cartographers. When these ultra-high-energy photons traverse intergalactic space, they don't travel in perfect straight lines. Weak but pervasive magnetic fields, threading through the cosmos like invisible spider silk, bend their trajectories ever so slightly. Meanwhile, the gravitational pull of dark matter clumps regions where space-time curves more sharply, further distorts their path. Veritas measures these deflections by comparing the arrival directions of gamma rays to the known positions of their sources, typically active galaxies called blazars. The discrepancies form a kind of celestial connect the dots, revealing where and how the universe's invisible scaffolding warps the paths of these photons. The real magic happens in the data patterns. Gamma rays of different energies get bent by varying amounts, like how a prism splits sunlight into colors, allowing scientists to reconstruct the strength and structure of intergalactic magnetic fields. In 2018, Veritas made headlines when it detected gamma rays from a blazar 4 billion light-years away whose arrival angles didn't match expectations. The deviation suggested something astonishing. The photons had passed through a previously unknown filament of the cosmic web, a vast, dark matter-rich structure linking galaxy clusters. It was like finding a hidden mountain range by watching how distant starlight bends around its peaks. But Veritas' discoveries go beyond mapping. Some gamma rays appear to lose energy during their journey in ways that defy conventional physics. One leading theory: they might be interacting with quantum foam, the hypothetical grainy texture of space-time at the smallest scales predicted by some theories of quantum gravity. If confirmed, this could provide the first experimental clues that space-time isn't smooth, but pixelated at the Planck length, a scale a billion times smaller than a proton. Other anomalies in the data might hint at action, like particles candidates for dark matter, that could convert gamma rays into invisible particles and back again as they traverse magnetic fields. The observatory's design is a marvel of adaptation. Each of its 12-meter mirrors, covered in hundreds of hexagonal segments, captures the fleeting blue flashes created when gamma rays collide with atmospheric molecules. Ultra-fast cameras record these air showers at nanosecond resolution, allowing computers to reconstruct the original gamma rays' direction and energy with pinpoint accuracy. Recent upgrades have boosted Veritas' sensitivity to gamma rays below 100 GeV, the energy range where intergalactic magnetic fields exert their most noticeable effects, turning it into a precision instrument for probing space-time's subtle curvature. What's often overlooked is how these observations bridge cosmic scales. The same magnetic fields that bend gamma rays also shape the evolution of galaxies, while the dark matter concentrations they reveal dictate where and how galaxies cluster. Future projects like the Cherenkov Telescope Array with its hundreds of detectors spread across hemispheres will expand this work exponentially, potentially creating the first full 3D map of the universe's magnetic skeleton. Until then, Veritas stands as a testament to human ingenuity using particles born in the fury of supermassive black holes to illuminate the invisible architecture of everything. The James Webb Space Telescope isn't just rewriting astronomy textbooks, it's flipping through the universe's oldest photo album, revealing snapshots of space-time when it was barely a toddler. In July 2022, when JWST unveiled its first deep field image, it wasn't merely showcasing distant galaxies. It was capturing light that had traveled for over 13 billion years, emitted when the cosmos was less than 5% of its current age. These primordial galaxies, glowing like embers in the infrared, aren't just pretty pictures, they're stress tests for our understanding of cosmic evolution, probing whether gravity and space-time behave differently in the universe's fiery youth. What makes these observations revolutionary isn't just the distance they cover, but the anomalies they've uncovered. Among those ancient galaxies, JWST found giants, cosmic titans far more massive and structured than our models predicted for such an early epoch. According to standard cosmology, the universe needed billions of years for gravity to sculpt tiny density fluctuations into sprawling galaxies. Yet here were fully formed behemoths, some weighing as much as 100 billion suns, appearing barely 300 million years after the Big Bang. It's like finding a skyscraper in the ruins of a Stone Age village, forcing astronomers to question whether early space-time allowed matter to clump faster than we thought, or if dark energy's repulsive force operated differently in the past. The secret to JWST time-traveling vision lies in its infrared eyes. As the universe expands, light from the earliest galaxies stretches into longer, redder wavelengths, a phenomenon called redshift. Some of these photons arrive with redshifts above 10, meaning the space they've traversed has stretched by over 1,000% during their journey. By analyzing this stretched light, scientists can measure how space-time itself ballooned across different eras. But here's where things get thorny. Preliminary JWST data suggests these ancient galaxies cluster in ways that slightly deviate from predictions based on the cosmic microwave background. Could this hint at exotic physics like dark matter interacting with itself in the early universe, or space-time expanding in fits and starts rather than a smooth acceleration? Zoom in on one of those galaxies and the mysteries multiply. Spectra from JWST NIR SPEC instrument reveal chemical fingerprints of heavy elements like oxygen and carbon in galaxies that, by conventional timelines, shouldn't have had time to forge them. Stars manufacture these elements through nuclear fusion, then scatter them in supernova explosions, a process requiring multiple stellar generations. Their premature presence suggests either that the first stars formed in a frantic burst we've yet to model, or that the primordial universe hosted pathways to heavy element production we've never considered. Yet JWST's greatest gift might be how it lets us watch cosmic dawn in motion. Unlike Hubble's deep fields, which were static snapshots, Webb's repeated observations of patches like the extended Groth strip allow astronomers to track subtle changes over time, not in individual stars, but in the statistical properties of galaxy populations. Already, these surveys have spotted candidate dark stars, hypothetical early behemoths powered by dark matter annihilation, rather than nuclear fusion whose bizarre light curves defy conventional classification. Other targets show gravitational lenses so extreme they bend background galaxies into perfect Einstein rings, providing natural telescopes to magnify even further into the past. The implications ripple across physics. If space-time expanded faster in certain epochs, it might explain why the universe's large-scale structure appears lumpier than simulations predict. Alternatively, modified gravity theories like MUND, which tweak Einstein's equations, could find new support if JWST confirms anomalous galactic rotations at these early times. Even string theory gets a nod. Some models suggest extra dimensions could have been more pronounced in the high-energy early universe, subtly altering how gravity sculpted those first structures. Every pixel in JWST deep fields is a time capsule holding clues to space-time's childhood. And as the telescope peers deeper still toward redshifts of 15 or 20, we might finally glimpse the universe's very first starlight photons that began their voyage when reality itself was still learning how to bend. Hovering over Antarctica on a high-altitude balloon, the Anita detector wasn't built to look down until it caught cosmic rays breaking the rules of physics. Between 2006 and 2016, this unusual observatory spotted something that shouldn't exist: ultra-high-energy tau neutrinos shooting upward from Earth's interior, as if the planet itself had become a particle accelerator. These weren't your average cosmic rays, packing energies over 500 trillion electron volts, enough to power a small city for a second. They should have been absorbed long before reaching Anita sensors. Yet there they were, emerging from below with trajectories suggesting they'd traversed thousands of miles of solid rock without a scratch. The implications sent shockwaves through particle physics. Neutrinos, famously ghostly, can pass through planets, but at these energies, the odds are astronomically low. It's like firing a bullet through a mountain and finding it intact on the other side. Even stranger, Anita detected these events while flying at 37 kilometers altitude, where Earth's curvature means any upward-moving particle must have entered through the planet's crust. Standard models suggested fewer than 1 in 100 million such neutrinos could survive the journey. Yet Anita recorded multiple candidates, sparking wild theories. Could these particles be evidence of sterile neutrinos, hypothetical shadow variants that barely interact with normal matter? Or perhaps signatures of cosmic strings, exotic space-time defects left over from the Big Bang, warping particle paths like invisible funnels? One particularly audacious idea ties the anomaly to dark matter. If our planet's core harbors dense clusters of these invisible particles, their occasional collisions might produce bursts of high-energy neutrinos. Alternatively, some models suggest the particles Anita detected weren't neutrinos at all, but a new type of matter that interacts only through gravity, a hypothetical tau-slepton from supersymmetry theory. The detector's unique vantage point was key. Most neutrino observatories, like Ice Cube buried in Antarctic ice, look downward for particles raining from space. Anita's upward view turned convention on its head, catching particles that seemingly defied absorption physics. Critics argue the signals could be mundane glitches from atmospheric noise or reflections off ice sheets. But the statistical unlikelihood of such mimics, combined with corroborating detections by Ice Cube of similar anomalous events, keeps the mystery alive. Future experiments like PUO, Anita's successor, aim to settle the debate with improved sensitivity. Meanwhile, theorists continue exploring how these rogue particles might fit into larger puzzles, from quantum gravity to the universe's matter-antimatter asymmetry. What makes Anita's findings so compelling isn't just the particles themselves, it's the reminder that even well-trodden ground, quite literally beneath our feet, might hide portals to undiscovered physics. Whether the final answer points to sterile neutrinos, dark matter decays, or space-time's hidden fractures, one lesson is clear: sometimes the universe's boldest clues come from the least expected directions. Deep beneath the Illinois prairie, A ring of superconducting magnets large enough to encircle a house holds the key to one of physics' most tantalizing mysteries. The Muon G2 experiment at Fermilab isn't just studying subatomic particles, it's hunting for tremors in reality's foundation. Muons, the heavier cousins of electrons, should wobble at a very specific rate as they spin in a magnetic field, a value calculated to 12 decimal places by the Standard Model. But when scientists measured this spin precession with unprecedented precision, the particles betrayed a whisper of difference, a discrepancy smaller than a gnat's wingbeat, yet potentially big enough to crack open physics rulebook. This minuscule anomaly, just 2.5 parts in a billion, might not sound earth-shaking until you realize what it implies. Muons exist in a quantum froth, constantly exchanging virtual particles with the surrounding vacuum. If their wobble doesn't match predictions, it suggests something invisible is tweaking the foam's texture, perhaps undiscovered particles popping in and out of existence, or forces that don't fit our current understanding of space-time's quantum structure. Picture stirring honey into tea and finding the spoon tilting slightly more than expected. You'd suspect hidden currents beneath the surface. That's precisely what Fermilab's researchers are confronting, only instead of honey, they're probing the fabric of reality itself. The experiment's design is a masterpiece of precision. Muons, created by slamming protons into a target, get injected into a 15-meter-wide storage ring where superconducting magnets keep them circling at nearly light speed. As they decay into electrons, detectors track the direction of these daughter particles, a proxy for the muon's spin orientation. Over billions of orbits, tiny deviations accumulate into measurable signals. The 2021 results, confirming earlier hints from Brookhaven National Lab, sent shockwaves through physics because they matched neither experimental error nor any standard model tweak. What makes this wobble so revolutionary are the possibilities it opens. One leading explanation involves hypothetical particles called leptoquarks or Z-prime bosons, exotic carriers of force that could mediate interactions between known particles in novel ways. Others speculate about extra dimensions curled up at microscopic scales, where unseen physics alters quantum behavior. The wildest theories suggest this anomaly might be our first peek into dark sector particles, a shadow universe of matter that communicates with ours only through gravity and subtle quantum effects. But the real magic lies in how this experiment bridges scales. Muons live for just 2.2 microseconds, yet their fleeting wobble could illuminate structures spanning the cosmos. If dark matter particles interact through the same hidden forces affecting muons, it might explain why they're so elusive. Alternatively, the anomaly could hint at why the universe contains more matter than antimatter, a crucial imbalance allowing our existence. Future measurements aim to have the uncertainty, potentially revealing whether this is a statistical fluke or the tip of a subatomic iceberg. What began as a test of quantum theory has become a referendum on reality's rulebook. Whether the final answer points to new particles, hidden dimensions, or something stranger still, one thing is certain: the quantum foam is fizzing with secrets we've only begun to fathom. Every night atop Cerro Tololo in Chile, a 570-megapixel camera stares into the cosmos, capturing not just light but the universe's accelerating heartbeat. The Dark Energy Survey doesn't just photograph galaxies, it chronicles space-time's silent rebellion against gravity's pull, mapping how dark energy, that enigmatic force making up 68% of the cosmos, stretches the very fabric of reality. Since 2013, this international collaboration has scrutinized 300 million galaxies across 1/8 of the sky, measuring their distribution and shapes with such precision it can detect distortions smaller than a hair's width seen from a mile away. But here's the twist: those distortions aren't flaws in the images. They're cosmic fingerprints warped by dark matter's gravity and stretched by dark energy's relentless push. The magic lies in two techniques borrowed from Einstein's playbook. First, weak gravitational lensing, where light from distant galaxies bends ever so slightly as it passes through massive clumps of dark matter, like a straw appearing bent in a glass of water. By analyzing these subtle shears across millions of galaxies, researchers reconstruct the invisible scaffolding of the cosmic web. Second, Baryon acoustic oscillations, frozen ripples from the early universe that now serve as a standard ruler. These ancient sound waves, imprinted when the cosmos was a seething plasma, today appear as a preferred distance between galaxy clusters. By measuring how this scale changes across cosmic time, scientists can track how dark energy's influence has grown. What makes the survey revolutionary isn't just its scale, but its ability to cross-check these methods against supernova data. The same technique that first revealed cosmic acceleration in 1998. When combined, these probes form a cosmic triangulation, revealing dark energy's properties with unprecedented clarity. Early results delivered a bombshell. The data favors a cosmological constant, Einstein's greatest blunder, resurrected where dark energy's strength remains unchanged over time. This contradicts some theories predicting it should weaken or strengthen as the universe expands. Yet mysteries linger. The survey's latest maps show the universe's structure is slightly smoother than simulations predict, as if dark energy began acting earlier than expected. Some speculate this could hint at modified gravity theories, where Einstein's equations break down at cosmic scales. Others wonder if dark energy interacts with dark matter in ways we've yet to imagine. Future data releases will delve deeper into these anomalies, potentially revealing whether dark energy is truly constant or a dynamic field evolving with the cosmos. Beyond the physics, the project's legacy lies in its collaborative ingenuity. To process 50 terabytes of raw images, teams developed novel machine learning tools to classify galaxies and filter atmospheric noise. Their algorithms now aid everything from medical imaging to wildfire prediction. Meanwhile, the survey's public data has spawned over 700 studies, from tracking near-Earth asteroids to studying galaxy evolution. As the next generation of telescopes like Rubin observatories LSST prepare to take the baton, one truth emerges: dark energy isn't just stretching space, it's stretching our understanding of reality. And with every new map, we're not just charting the cosmos, we're decoding the invisible hand shaping its fate. Perched high on the frozen plateau of the South Pole, where the air is so thin and dry it barely distorts starlight, the Bicep and Keck Array telescopes stare unblinking at the oldest light in existence, not to see it, but to read the secret handwriting gravity has left upon it. These instruments aren't your typical observatories. Instead of lenses and mirrors, they're armed with arrays of superconducting detectors chilled to near absolute zero, designed to catch whispers from the universe's first trillionth of a second, encoded in the cosmic microwave background's polarization. What they're hunting for isn't just ancient light, it's the faintest spiraling patterns in that light. The telltale curls that could prove space-time itself was once shaken by primordial gravitational waves from the Big Bang's inflationary frenzy. Imagine the newborn universe, a seething quantum foam where space-time itself writhed with violent fluctuations. Inflation, the theory that the cosmos underwent a momentary exponential growth spurt, predicts that these microscopic tremors would have been stretched to cosmic proportions, imprinting their signature as gravitational waves that still ripple through the fabric of reality today. If those waves exist, they'd leave a distinctive swirl in the CMB's polarization, a pattern called B-mode polarization. Spotting it would be like finding the fossilized footprints of the universe's first steps. The challenge: these signals are absurdly faint. The B-mode polarization from inflation is maybe 1 part in 10 million of the CMB's total signal, buried under interference from galactic dust and other astrophysical noise. That's why BICEP and Keck operate at the South Pole, the coldest, driest place on Earth, where atmospheric interference is minimal. Their detectors, some of the most sensitive ever built, can discern temperature variations of a few millionths of a degree. In 2014, the BICEP-2 team thought they'd struck gold, announcing a detection of B modes that made global headlines. But further analysis revealed a cruel twist. Much of the signal came from interstellar dust in our own galaxy, not primordial inflation. Yet the hunt didn't end there. The Keck array, BICEP's successor, has since refined the search with multiple frequencies to filter out dust contamination. Each incremental improvement peels back another layer of cosmic static, inching closer to the inflationary signal. The stakes couldn't be higher. If detected, these B modes wouldn't just confirm inflation, they'd reveal the energy scale at which it occurred, offering clues about the unification of quantum mechanics and gravity. Some models even suggest the pattern could hint at extra dimensions or the quantum nature of space-time itself. What's often overlooked is how this experiment ties the unimaginably small to the cosmological. Those hypothetical gravitational waves arose from quantum fluctuations smaller than a proton, stretched to scales larger than galaxy clusters by inflation. Their detection would bridge the chasm between particle physics and cosmology, offering a glimpse of physics at energies 1 trillion times beyond what any collider could reach. Future upgrades, like the upcoming BICEP array, will push sensitivities even further, turning the South Pole's icy silence into the ultimate listening post for the universe's birth cries. The true brilliance of this experiment lies in its patience. Unlike colliders that create new particles in violent collisions, BICEP and Keck are archaeologists of the sky, sifting through ancient light for echoes of an epoch when the entire observable universe was smaller than an atom. And if they succeed, they won't just rewrite cosmology textbooks, they'll hand us a time machine, letting us peer past the edge of what we thought was knowable. Gravity's faintest whispers demand the quietest of laboratories, so quiet, in fact, that Earth itself is too loud to hear them. That's why in 2015, the European Space Agency launched LISA Pathfinder, a spacecraft with one audacious goal: to float 2 gold-platinum cubes in perfect free fall, shielded from every force in the universe except gravity itself. This wasn't just an engineering marvel, it was a dress rehearsal for humanity's next great observatory, one that won't study light but the ripples in space-time from collisions so colossal they shake the fabric of the cosmos. And what LISA Pathfinder proved is nothing short of miraculous: that we can detect movements smaller than the width of an atom's nucleus across a distance of 1 million kilometers. At the heart of this mission lay a deceptively simple test. 2 identical cubes, each the size of a Rubik's Cube but far more perfect, were placed in near-perfect isolation inside the spacecraft. The idea: if you could shield these cubes from all non-gravitational forces, solar wind, magnetic fields, even the faint pressure of sunlight, they would follow what physicists call pure geodesic motion, tracing the unaltered curves of space-time like marbles rolling on a stretched bedsheet. The spacecraft's job was to hover around the cubes without touching them, using microscopic thrusters to adjust its position based on laser measurements of the cube's movements. The precision required was staggering. To detect gravitational waves from distant black hole mergers, future missions would need to measure changes in distance between these cubes as small as 20 picometers. That's less than the diameter of a helium atom. What LISA Pathfinder achieved surpassed even the rosiest predictions. The cubes remained motionless relative to each other to within 5 picometers per square root of a hertz, a level of stability so extreme it's like measuring the distance from New York to Los Angeles with an error no thicker than a human hair. But the real triumph wasn't just the precision, it was how the mission exposed the hidden noise floor of the universe. At these scales, even the faintest cosmic phenomena become deafening. The constant rain of cosmic rays jostling atoms in the cubes, the thermal vibrations of individual molecules on the spacecraft's surface, even the minuscule gravitational pull of the spacecraft's own wiring, all had to be accounted for. It's like trying to hear a pin drop during a hurricane, and LISA Pathfinder showed we could do it. Now, imagine scaling this up. LISA Pathfinder was merely a proof of concept, a single spacecraft monitoring 2 test masses over a span of 38 centimeters. Its successor, the Laser Interferometer Space Antenna LISA, will form a triangular constellation of 3 spacecraft, separated by 2.5 million kilometers, with each arm acting as one leg of a gravitational wave detector. When supermassive black holes merge in the centers of distant galaxies, their collisions will send space-time ripples coursing through the universe, stretching and compressing the distances between these spacecraft by mere atomic widths. LISA will catch these distortions, opening a window onto events that no optical telescope could ever see, like the universe's first black holes, or the cosmic strings that might thread the vacuum of space. What makes LISA Pathfinder's legacy so profound is how it redefines the possible. Before this mission, many doubted whether isolating objects from all forces except gravity could be achieved outside the realm of theory. Now we know not only that it's possible, but that the universe cooperates, that at these infinitesimal scales, space-time is smooth enough to trace its faintest tremors. Future missions might one day listen for gravitational echoes from the Big Bang itself, or catch the space-time ripples produced by defects in the universe's earliest geometry. And it all started with 2 silent cubes floating in the dark, teaching us how to hear the music of the cosmos. Somewhere in the vast stretches between galaxies, invisible threads of matter and energy are subtly combing through bursts of radio waves like cosmic sieves, and the CHIME telescope in British Columbia is decoding their secrets. Fast radio bursts, those enigmatic millisecond flashes of energy from deep space, aren't just cosmic oddities, they're messengers carrying encrypted details about the universe's hidden scaffolding. When one of these bursts races across billions of light years, it doesn't travel through empty space. It slices through clouds of ionized gas, dark matter halos, and the tenuous plasma suffusing galaxy clusters, each leaving a telltale delay in the burst's arrival time. CHIME, with its 4 half-cylinder reflectors resembling snowboarding ramps, catches these dispersed signals and unpacks their delays like a detective analyzing fingerprints at a crime scene. What makes these bursts so revealing is their dispersion measure, the degree to which their lower frequency components lag behind the higher ones. This stagger isn't random noise, it's a cumulative receipt of every electron cloud the burst encountered en route. Think of it as cosmic echolocation. By measuring how much the burst's frequencies have spread, astronomers can tally the total electrons along its path, mapping the otherwise invisible distribution of matter across intergalactic space. In 2019, CHIME detection of a repeating burst from a distant galaxy provided the first chance to compare dispersion measures across multiple signals from the same source. The variations hinted at turbulent, magnetized regions surrounding the burst's origin, possibly a neutron star orbiting a black hole, its environment warping space-time like a funhouse mirror. But here's where it gets even wilder. Some bursts show dispersion patterns that don't quite match predictions based on known matter distributions, one leading theory. These anomalies might trace the gravitational echoes of cosmic strings, hypothetical defects in space-time left over from the universe's earliest moments. These ultra-dense, thread-like structures, if they exist, would bend space-time around them like cracks in ice, subtly altering the path and timing of passing radio waves. CHIME ability to pinpoint burst locations to within arcminutes allows astronomers to cross-reference these events with gravitational lensing maps, hunting for overlaps where space-time's curvature might have left a signature. The telescope's design is as unconventional as its targets. Unlike traditional dishes that pivot to track objects, CHIME stares fixedly at the sky, relying on Earth's rotation to sweep its field of view. Its 1,000-antenna array and real-time signal processing can sift through a petabyte of data daily, equivalent to streaming every movie ever made in HD twice. This relentless gaze has turned CHIME into a fast radio burst factory, discovering hundreds of events since its 2017 debut, including ultra-rare bursts from our own galaxy that helped confirm Magnetar's highly magnetized neutron stars as at least one source of these cosmic flashes. Yet the most tantalizing possibility lies in what these bursts might say about dark matter. If certain types of hypothetical particles, like actions, permeate space, they could interact with the burst's radio waves in ways that imprint subtle polarization twists. CHIME polarization measurements are already refining these searches, narrowing down the properties of potential dark matter candidates. Future upgrades, like the proposed CHIME/FRB Outriggers project, will triangulate bursts with even sharper precision, turning each one into a probe of cosmic structure at scales no optical survey could match. What began as a quest to solve a radio astronomy puzzle has become something far grander, a new way to weigh the universe, measure its hidden geometry, and maybe even eavesdrop on space-time's most elusive defects. And with every millisecond burst CHIME captures, we're not just hearing cosmic static, we're decoding the universe's hidden diary, written in the language of delayed radio waves. Buried deep beneath the Antarctic ice, where temperatures plunge to -58 degrees and sunlight never reaches, lies one of the most unusual telescopes ever built, one that doesn't look up at the sky but down through the Earth itself. The Ice Cube Neutrino Observatory isn't designed to catch light, but something far more elusive. Neutrinos, the universe's ghostly messengers that pass effortlessly through planets as if they weren't there. Spanning a cubic kilometer of pristine ice, this labyrinth of over 5,000 optical sensors waits patiently for the rare moment when one of these phantom particles crashes into an atom, producing a fleeting blue flash, the only sign of a cosmic journey that may have lasted billions of years. What makes IceCube revolutionary isn't just its scale, but its targets. Unlike photons that scatter or get absorbed, neutrinos travel in straight lines from their sources, carrying undistorted information across cosmic distances. When a high-energy neutrino slams into the ice, it creates a secondary particle called a muon, moving faster than light can travel through ice, an optical shockwave called Cherenkov radiation. The sensors capture this faint glow, allowing physicists to reconstruct the neutrino's energy and direction with surprising precision. Some of these particles pack energies millions of times greater than those produced in human-made colliders, and they've come from places no telescope can peer into, like the hearts of active galaxies or the aftermath of colliding neutron stars. But here's where space-time's fingerprints emerge. As these neutrinos traverse the universe, their oscillations shifts between different flavors, like electron, muon, and tau, could be subtly altered by the warped geometry around black holes or the expansion of the cosmos itself. Imagine rolling a marble across a stretched rubber sheet. Its path bends with the sheet's contours. Similarly, neutrinos passing through dense galaxy clusters or near cosmic voids might experience minute changes in their behavior, betraying the hidden structure of space-time along their route. In 2018, IceCube made history by tracing one such neutrino back to a blazar 4 billion light-years away, a feat that earned it the nickname the first neutrino telescope. The real magic lies in what these detections reveal about extremes. The highest energy neutrinos IceCube catches likely originate in environments where space-time is stretched to its limits near supermassive black holes or relativistic jets where matter moves at 99.9% the speed of light. By studying how these particles interact with the ice, scientists can indirectly probe conditions where gravity and quantum mechanics collide. Some theories even suggest that neutrinos might behave differently in regions of intense curvature, offering clues about how to reconcile Einstein's relativity with the quantum world. Yet IceCube's most tantalizing discoveries might still lie ahead. Upgrades like IceCube Gen 2 will expand the detector's volume, increasing its chances of catching neutrinos from rare events like supernova shockwaves or the annihilation of dark matter. Others propose using the Moon's radio-quiet far side as a neutrino detector, listening for the faint pulses these particles would generate in lunar rock. With each new detection, we're not just studying particles, we're mapping the universe's hidden architecture, one ghostly flash at a time. The Event Horizon Telescope's iconic first image of a black hole in Messier 87 was just the opening act. Now its lenses are turning toward a far more tempestuous target, Sagittarius, a star, the supermassive black hole lurking at the heart of our own Milky Way. While M87's black hole posed for its portrait with eerie serenity, Sagittarius, a star, is a cosmic berserker, devouring matter in violent outbursts that flare across the electromagnetic spectrum. This isn't just another observation, it's a test of whether all singularities bend space-time by the same rules, or if each leaves its own gravitational fingerprint on the fabric of reality. At first glance, Sagittarius, a star, should be easier to image than its distant cousin. It's 20 times closer, just 27,000 light-years away compared to M87's 55 million. But proximity comes with complications. Our galaxy's central black hole, though 4 million times the Sun's mass, is a lightweight compared to M87's 6.5 billion solar mass behemoth. That means Sagittarius, a star's event horizon, appears smaller in the sky, like trying to photograph a grapefruit on the Moon instead of a watermelon. Worse, our view is obscured by thick clouds of interstellar dust and plasma that scatter radio waves, forcing astronomers to develop novel algorithms to peel back the noise. Yet the payoff could rewrite astrophysics. Unlike M87's relatively placid disk, Sagittarius, a star's accretion, churns with turbulence. Some theories predict this chaos should warp space-time differently than a calm black hole, imprinting unique distortions on the shadow's edge. Imagine dropping two stones into a pond, one gently, one with force. Both create ripples, but the patterns differ. Similarly, if Sagittarius, a star's shadow, shows unexpected asymmetries or flickering compared to M87's, it might reveal how a black hole's diet affects its gravitational field. There's also the mystery of Sagittarius, a star's spin. General relativity predicts a rotating black hole drags space-time around it like a whirlpool, an effect that should subtly alter the shape of its photon ring, the bright circle of light orbiting just outside the event horizon. Current estimates suggest our galactic center, black hole, spins at about 60% of its maximum possible rate, but the Event Horizon Telescope's images could measure this directly by analyzing how the photon ring's thickness varies. A confirmed mismatch with M87's spin signature would prove that singularities aren't all cut from the same cosmic cloth, the most tantalizing possibility. Spotting flares near the event horizon. Sagittarius, a star, regularly erupts in X-ray bursts as it shreds passing gas clouds or stars. If the telescope catches one of these fireworks in progress, it could reveal how space-time rebounds from such violent feedings. Some models suggest these flares might momentarily brighten the photon ring in predictable ways, offering a real-time lab to test how energy propagates through warped space. Other theories propose that flares could briefly distort the black hole's shadow, like a stone momentarily altering a pond's surface tension. But the grandest question looms largest: does Sagittarius, a star, obey Einstein's equations as faithfully as M87 did? Any deviation in its shadow's size or shape might hint at exotic physics, extra dimensions curled up near the singularity, quantum gravity effects smoothing out the predicted infinite curvature, or even relics from the black hole's formation era frozen into its space-time structure. The data could also settle debates about whether black holes truly erase information, a paradox that's divided physicists for decades. As the Event Horizon Telescope's network expands to include new antennas in Africa and Greenland, its vision grows sharper. Future observations might even track stars like S2, which orbits Sagittarius, a star, every 16 years, to see if their light bends precisely as relativity predicts when passing near the black hole's crushing gravity. Each new image isn't just a snapshot, it's a page in the universe's playbook, teaching us how space-time dances under the most extreme conditions imaginable. And if Sagittarius, a star's performance differs from M87's, we might need to rewrite the choreography entirely. While LIGO and Virgo have revolutionized our ability to detect gravitational waves from colliding black holes and neutron stars, their Earth-bound designs leave an entire spectrum of cosmic ripples untouched, frequencies too low for ground-based instruments to catch. That's where China's Tianqin mission comes in, a space-based gravitational wave observatory designed to listen for the universe's deepest, slowest vibrations. Imagine trying to hear a whale's song with a microphone tuned only for bird chirps. That's the challenge facing current detectors when it comes to low-frequency waves. Tianqin, whose name translates to celestial harp, aims to string its instruments across space itself, with 3 satellites forming a triangular constellation orbiting Earth, each separated by 170,000 kilometers. A detector so vast it could wrap around our planet 4 times over. Unlike LIGO kilometer-scale arms, which sense high-frequency waves from violent mergers, Tianqin's laser-linked satellites will hunt for oscillations with periods of hours to years, the kind produced by supermassive black holes dancing toward collision in the hearts of distant galaxies. These cosmic behemoths, weighing millions or even billions of suns, generate space-time ripples too base-heavy for ground observatories, but their slow, stately orbits before merging could reveal secrets about how galaxies evolve, how dark matter clusters around them, and even whether Einstein's equations hold true under such extreme conditions. The mission's design is a marvel of precision. Each satellite must maintain near-perfect free-fall motion, shielded from solar wind and other disturbances by drag-free technology so sensitive it can detect acceleration changes smaller than 1/1,000,000th of Earth's gravity. What sets Tianqin apart isn't just its frequency range, it's the new physics it might uncover. Some theories predict that supermassive black hole binaries should be common, yet few have been observed. Are they shrouded in dust, or could their gravitational waves reveal unexpected dynamics, like hidden third companions or warped space-time geometries? Tianqin could also spot intermediate mass black holes, the elusive, missing link between stellar and supermassive varieties, by their telltale gravitational hum as they orbit larger partners. And if cosmic strings exist, those hypothetical defects in space-time left over from the Big Bang, their ultra-low-frequency vibrations might finally register on Tianqin's celestial stethoscope. The mission's roadmap is as ambitious as its science. Before launching the full constellation around 2035, China plans a Pathfinder satellite to test key technologies, including a groundbreaking inertial sensor that can measure displacements at the picometer scale, less than the width of an atom. Success would position Tianqin alongside LISA, Europe's planned space-based detector, creating a gravitational wave network spanning multiple frequency bands. Together, these observatories could cross-validate detections, much like radio and optical telescopes collaborate today. But perhaps Tianqin's boldest promise lies in probing the universe's earliest epochs. The lowest frequency gravitational waves might carry echoes from cosmic inflation, that brief moment when the universe expanded exponentially faster than light. These primordial ripples, far older than the cosmic microwave background, could reveal energy scales 1 trillion times beyond what any particle collider can reach. It's a reminder that sometimes, to hear the universe's faintest whispers, you need to leave the noise of Earth behind and listen from the quiet of space. Forget Hollywood's asteroid-deflecting heroes. NASA, a DART mission proved we could nudge a celestial body with nothing but precision engineering and Newton's third law. In September 2022, the double asteroid redirection test spacecraft slammed into Dimorphos, a small moonlet orbiting the asteroid Didymos at 14,000 miles per hour. The impact wasn't just a planetary defense trial. It was a real-time experiment in how mass redistributions warp space-time on a local scale. By measuring how Dimorphos's orbit around Didymos changed post-collision shortening by a staggering 32 minutes, scientists gained unprecedented data on how kinetic energy alters the gravitational dance between two bodies. Think of it as throwing a pebble into a pond and watching how the ripples affect nearby floating leaves, except here, the pond is the fabric of space-time itself, and the leaves are asteroids locked in a mutual gravitational embrace. But the real space-time twist lies in the aftermath. The collision ejected over 2 million pounds of debris, creating a comet-like tail that stretched 6,000 miles. This ejected material didn't just drift away harmlessly, it carried momentum, acting like a natural rocket thruster that further tweaked Dimorphos's orbit through the Yarkovsky effect. Here's the kicker: that debris cloud temporarily altered the local gravitational field around the asteroid system, a subtle distortion measurable by telescopes tracking the asteroid's positions. It's a phenomenon Einstein would have adored, a visible demonstration of how mass and energy, whether in the form of a spacecraft or scattered rock, bend the stage on which celestial mechanics plays out. Now pair this with NASA's Psyche mission, launching toward a metallic asteroid of the same name in 2023. Unlike rocky or icy bodies, Psyche is thought to be the exposed core of a protoplanet, a chunk of iron-nickel so dense its gravity field could reveal how ultra-high mass concentrations distort space-time differently than diffuse objects. The spacecraft's gamma-ray spectrometer will map the asteroid's composition, while precise radio tracking measures how its uneven mass tugs on the probe's orbit. If Psyche's core has regions of extreme density like metallic pockets from ancient impacts, they could create minute space-time wrinkles detectable in the spacecraft's trajectory. These measurements might even hint at whether compact metals warp gravity differently than theoretical models predict, a test of general relativity in environments we've never probed before. What makes these missions revolutionary isn't just their individual goals, it's how they complement each other. DART shows how we can actively manipulate local space-time geometry through brute force, while Psyche explores how nature's own heavy elements do it passively over eons. Together, they're teaching us that gravity isn't just a backdrop to cosmic events, it's a dynamic, malleable player in them. Future missions might use these insights to refine asteroid deflection strategies or even harness gravitational anomalies for navigation. After all, if we can predict how space-time bends around a nickel-iron asteroid, why not use similar principles to steer spacecraft through cluttered solar systems? The ultimate lesson, from planetary defense to probing primordial metal worlds, humanity is no longer just observing gravity's rules, we're learning to rewrite them. High atop Chile's Atacama Desert, where the air is so thin and dry it barely blurs the stars, a new generation of telescopes is preparing to read the universe's oldest love letter. The cosmic microwave background, with sensitivity so sharp it could spot a snowflake's shadow on the moon. The Simons Observatory isn't just another array of antennas. It's a time machine tuned to the faintest whispers from the universe's first trillionth of a second, hunting for space-time ripples that could rewrite everything we know about existence. With over 60,000 detectors chilled to near absolute zero, this sprawling network of dishes and cameras will map the CMB's polarization with 50 times the resolution of its predecessors, searching for patterns that might betray the presence of other universes or reveal that our cosmos is locked in an endless cycle of rebirth. What makes this experiment revolutionary isn't just its scale, it's the questions it dares to ask. When the universe was a seething quantum foam moments after the Big Bang, microscopic fluctuations in space-time were stretched to cosmic proportions by inflation, imprinting their signatures as faint curls in the CMB's polarization. These B-mode patterns, if detected, would be the smoking gun of primordial gravitational waves, but the Simons team is probing even deeper. Some theories suggest these ripples might carry subtle anomalies, like statistical fingerprints of collisions between our universe and neighboring bubble universes in the multiverse. Others predict repeating patterns that could hint at a cyclical cosmos, where each Big Bang is preceded by a big crunch. The observatory's ultra-low-noise amplifiers and superconducting cameras are designed to tease out these whispers from the static of interstellar dust and galactic synchrotron radiation, filtering cosmic noise with precision akin to isolating a single violin's note in a symphony of hurricanes. But here's where the real magic happens. The observatory's small aperture telescopes will scan wide swaths of sky to capture the grand architecture of inflation's echoes, while its large aperture counterparts zoom in on patches where primordial signals are strongest. This dual approach mirrors a photographer using both a wide-angle lens and a macro lens at once, revealing both the forest and the individual leaves, one target. The reionization bump, a faint polarization signal from when the universe's first stars ignited, flooding space with ultraviolet light that stripped electrons from atoms. This epoch, 500 million years after the Big Bang, left its own wrinkles in the CMB's fabric, and comparing them to the primordial patterns could reveal how gravity's grip evolved as the cosmos matured. The stakes transcend mere cosmology. If the observatory detects evidence of cyclic universes, it would imply space-time can rebound from collapse like a phoenix from ashes, a radical departure from the standard inflationary narrative. Alternatively, multiverse signatures might show our universe as one bubble among infinite others, each with its own physical laws. Even null results would force theorists back to the drawing board, potentially dooming beloved models to the dustbin of history. The project's name honors the philanthropic foundation backing it, but it could just as well nod to mathematician David Hilbert's famous dictum, "We must know." We will know. As the first data trickles in by 2025, astronomers are already dreaming of next-generation upgrades arrays with millions of detectors, or space-based successors free of atmospheric interference. For now, the Simons Observatory stands as humanity's most sensitive ear pressed to the cosmos' chest, listening for the heartbeat of realities beyond our own. And in those faint, frozen ripples, we might just find the answer to the oldest question of all: where and what else is out there? The quest to unite quantum mechanics with gravity has spawned theories so bizarre they read like science fiction, each proposing a radically different vision of how space-time behaves at scales smaller than an atom. Take loop quantum gravity, where space isn't smooth but woven from microscopic threads, forming a dynamic fabric that can't be divided infinitely. Picture a T-shirt under a microscope. What seems like continuous fabric reveals itself as interlocking loops of thread. In this model, these quantum loops create space-time structure, with their interactions generating gravity itself. The theory makes a jaw-dropping prediction that black holes can't fully collapse into singularities but rebound as white holes, spewing out matter like a cosmic bounce. Future experiments could hunt for these rebounding remnants in ancient gamma-ray bursts or subtle anomalies in gravitational wave data from collisions. Then there's string theory, the grand contender where particles aren't points but vibrating strings, and space-time has 10 or 11 dimensions curled up too tightly to see. These extra dimensions could explain gravity's puzzling weakness compared to other forces. It might be leaking into hidden realms. String theory suggests wild tests, like searching for miniature black holes at particle colliders, signatures of extra dimensions, or detecting gravitational waves with unusual frequencies that higher dimensional resonances might produce. Some variants even predict space-time is a hologram, with all 3D reality encoded on a distant 2D surface, a notion the holometer experiment tried and failed to confirm, though future upgrades could revisit the idea with sharper precision. But the dark horse is causal dynamical triangulation, which imagines space-time as a mosaic of tiny geometric blocks that change shape over time. It's like building a universe from LIGO, each block a four-dimensional chunk of reality, snapping together in ways that avoid the infinite densities plaguing other theories. Supercomputer simulations of this model show space-time spontaneously organizing into the smooth cosmos we know, hinting that gravity might emerge from randomness, not fundamental force. Experimentalists are designing tabletop setups using ultra-cold atoms to mimic this blocky structure, watching how gravity emerges in their quantum simulators. The real breakthrough will come when we can probe these theories not just with math, but with observation. Next-generation gravitational wave detectors like the Einstein telescope or space-based LISA might catch echoes of quantum space-time foam in high-frequency ripples from the early universe. Atomic interferometers could measure if falling particles experience tiny, theory-specific deviations from Einstein's predictions. And if we ever detect violations of Lorentz invariance, subtle cracks in the speed of light rule, it could favor loop quantum gravity's granular space over string theory's smooth continuum. What's fascinating isn't just the theories' differences, but their shared implication that space-time isn't fundamental, but something deeper wearing a disguise. Whether it's loops, strings, or blocks, the message is clear: gravity's next revolution won't tweak Einstein's equations, but expose them as approximations of a wilder truth. And when experiments finally pick a winner, we won't just solve a physics problem, we'll rewrite reality's operating manual. Hidden in the quiet hum of powerful magnets and ultra-sensitive detectors, physicists are hunting for one of the universe's most elusive phantoms, the action. This hypothetical particle, originally proposed to solve a puzzle in quantum physics, might hold the key to two of science's greatest mysteries: the nature of dark matter and the quantum structure of space-time itself. Unlike the massive, sluggish particles once thought to make up dark matter, actions would be unimaginably light, potentially trillions of times less massive than electrons, yet so abundant they could permeate the cosmos like an invisible cosmic fog. And here's the twist: if actions exist, they wouldn't just pass through space unnoticed, they'd interact with it in ways that subtly warp the fabric of reality, leaving fingerprints we're now learning to detect. The search hinges on a bizarre quantum phenomenon called the Primarkov effect. In strong magnetic fields, actions should occasionally convert into photons, particles of light, and vice versa. Experiments like ADMCS at the University of Washington and CAP in South Korea exploit this by using superconducting magnets and ultra-cold microwave cavities to create environments where these conversions might occur. Picture a cosmic game of hide and seek. As dark matter actions stream through Earth, these detectors act like finely tuned radios, scanning millions of frequency channels for the faintest whisper of a photon appearing out of nowhere. The challenge: the expected signal is so weak it could easily drown in background noise, like trying to hear a single raindrop in a thunderstorm. But the real magic lies in how actions could bridge the quantum and cosmic scales. If these particles make up dark matter, their collective gravitational influence would shape galaxies and galaxy clusters, while their quantum behavior might imprint on space-time's finest structure. Some theories suggest actions could form macroscopic quantum states, creating rippling, action stars, or even topological defects in space-time itself, cosmic strings or domain walls woven from pure quantum field. These structures wouldn't just curve space-time like ordinary matter. They might introduce new types of distortions, warping the vacuum in ways general relativity never anticipated. Recent advances have turned this search into a full-spectrum effort. While microwave cavities hunt for actions in specific mass ranges, other experiments like CASPER use nuclear magnetic resonance to probe how action dark matter might subtly tweak the spin of atomic nuclei. Then there's the innovative approach of using telescopes like Hawk in Mexico, scanning gamma rays from distant neutron stars for excess emissions that could reveal actions converting to light in those extreme magnetic fields. Each method targets a different slice of the action parameter space, collectively painting the most detailed portrait yet of where this ghostly particle might hide. What makes this hunt so thrilling isn't just the potential payoff, it's how it forces us to rethink the boundaries of known physics. If actions exist, they'd be the first particles discovered that aren't part of the standard model, opening a portal to understanding why the universe has so little antimatter, or how quantum fields might have shaped the cosmos' infancy. And if they don't, their absence would steer physicists toward even wilder ideas, like hidden dimensions or entirely new forces. Either way, the action quest reminds us that the universe's deepest secrets often lurk in the quietest corners, where the hum of a magnet or the flicker of a photon might rewrite everything we know. Wormholes, those fantastical cosmic shortcuts beloved by science fiction, might not be as impossible as they seem. At least, that's what mathematicians and physicists are exploring in cutting-edge simulations that test whether these space-time tunnels could remain stable long enough to traverse. Unlike black holes, which crush everything that enters them, a traversable wormhole would theoretically allow matter and even spacecraft to pass through unharmed, connecting distant corners of the universe in an instant. But here's the catch. Einstein's equations suggest wormholes would collapse the moment anything tries to enter, snapped shut by their own gravity like a cosmic mousetrap. That's where exotic matter comes in, a hypothetical substance with negative energy density that could act as a kind of anti-gravity scaffolding, propping the wormhole open against its natural urge to implode. Recent simulations have pushed this idea into uncharted territory. By tweaking the parameters of general relativity, theorists have found that certain configurations of exotic matter, arranged in precise, donut-shaped rings around the wormhole's throat, might stabilize the tunnel long enough for a single, harrowing journey. Picture a subway tunnel reinforced against cave-ins, but instead of steel beams, the supports are made of quantum fields that defy normal physics. These models rely on conditions so extreme they border on the absurd. Matter with negative mass, space-time geometries twisted like Möbius strips, and energy densities that fluctuate in ways never seen in nature. Yet mathematically, they hold together. One particularly wild simulation even suggests that a wormhole could be stabilized by threading it with cosmic strings, hypothetical, infinitely thin filaments of pure energy left over from the Big Bang, acting like tension wires to keep the throat from pinching shut. The real breakthrough, though, isn't just in the math, it's in how these simulations are forcing us to rethink causality itself. A stable wormhole wouldn't just bend space, it could twist time, creating closed time-like curves that allow for time travel. That's where the equations get truly mind-bending. Some models show that any attempt to send information or matter through a wormhole would trigger quantum feedback loops, scrambling the signal into nonsense or vaporizing the tunnel entirely. It's as if the universe has a built-in paradox detector, collapsing wormholes the moment they threaten to break the rules of cause and effect. Yet for all their instability, wormholes refuse to vanish from serious scientific discussion. Advanced simulations now explore whether quantum entanglement, that spooky link between particles across vast distances, could play a role in stabilizing microscopic wormholes, effectively creating subatomic shortcuts through space-time. Others speculate that wormholes might naturally form in the chaotic foam of the quantum vacuum, flickering into existence for fractions of a second before vanishing again. If we could somehow capture and enlarge one of these fleeting structures, interstellar travel might not require generations-long voyages, but a single, daring leap through a cosmic backdoor. Of course, the gap between theory and reality remains vast. No one knows how to manufacture exotic matter or whether the laws of physics would even permit it. But the mere fact that wormholes haven't been mathematically ruled out is a triumph of human curiosity. Every simulation that doesn't end in catastrophic collapse brings us one step closer to understanding whether these cosmic shortcuts are the stuff of dreams or a future we might one day engineer. And if that day comes, the universe won't just feel smaller, it'll feel wide open. What if everything we see, every galaxy, planet, and atom, is just an elaborate cosmic illusion? The holographic principle turns reality inside out, suggesting our three-dimensional universe might be nothing more than a projection from information encoded on a distant two-dimensional surface. Think of it like a movie screen. The images appear to have depth and motion, but they're really just patterns of light painted onto a flat canvas. This isn't just wild speculation, it's a serious theory born from black hole physics, where the amount of information a black hole can hold scales with its surface area, not its volume. That bizarre observation led physicists like Gerard T. Hooft and Leonard Susskind to propose that the entire cosmos might operate the same way, with every event inside our universe somehow written on its outermost edge. Now, imagine testing this mind-bending idea. Future experiments could hunt for subtle glitches in reality, tiny pixelations or distortions that betray the universe's hidden 2D code. One approach involves scrutinizing the cosmic microwave background for anomalous patterns, like finding a watermark in the afterglow of the Big Bang. Another looks for unexpected noise in gravitational wave detectors, the kind that might arise if space-time has a fundamental resolution limit, like a digital image breaking down when zoomed in too far. Even quantum entanglement experiments might hold clues. If particles separated by vast distances respond to each other instantly, it could hint at a deeper, non-local connection, like 2 points on a hologram linked by the underlying code. The most audacious test might come from quantum gravity probes. If space-time truly emerges from a 2D surface, then at extremely small scales, think a billionth of the size of an atom, gravity should behave differently than Einstein predicted. Experiments like the holometer at Fermilab are already searching for this quantum jitter by bouncing lasers between mirrors spaced kilometers apart, hunting for fluctuations smaller than a proton. A confirmed detection wouldn't just validate the holographic principle. It would mean everything from supernova to your morning coffee is essentially a high-resolution projection from the edge of reality. What's truly staggering are the implications. If the universe is holographic, then concepts like distance and volume might be secondary, like shadows cast by a deeper structure. Black holes could be nature's way of compressing data, their event horizons acting like cosmic hard drives. Even time might lose its fundamental status, emerging only when we play the holograms encoded information in sequence. Future telescopes mapping the large-scale structure of the cosmos could look for statistical anomalies, patterns that resemble information compression or pixelation at cosmic scales. The holographic principle doesn't just challenge our intuition, it redefines what a real even means, and if experiments one day confirm it, we'll have to grapple with a truth far stranger than fiction, that the universe isn't just expanding or evolving, but rendering itself into existence moment by moment, like an infinite movie projected from the edges of the void. Time crystals sound like something straight out of a science fiction novel, structures that don't just exist in space, but pulse rhythmically in time, forever cycling without energy input. Yet these bizarre quantum systems are very real, first proposed by Nobel laureate Frank Wilczek in 2012, and later created in labs using chains of ions, superconducting qubits, and even diamonds with nitrogen vacancies. Unlike ordinary crystals which repeat their atomic patterns in space, time crystals break time translation symmetry, meaning their structure evolves in a predictable, repeating way, but doesn't settle into equilibrium like everything else in the universe. It's as if you nudged a pendulum and instead of slowing down, it kept swinging at the same rhythm indefinitely, defying the laws of thermodynamics. The key to this defiance lies in quantum entanglement. In a time crystal, particles become so intricately linked that their collective behavior locks into a stable oscillation, even without external energy. Imagine a row of dominoes that, once tipped, don't just fall in a line but begin flipping back and forth endlessly, their motion sustained by an invisible quantum choreography. This behavior was first observed in 2017 by 2 independent teams, one at Harvard using ytterbium ions, another at the University of Maryland using chains of trapped atoms, both confirming that time crystals aren't just theoretical curiosities, but observable phenomena. What makes time crystals revolutionary isn't just their defiance of equilibrium, it's how they challenge our understanding of space-time's symmetries. Einstein's relativity assumes the laws of physics are the same everywhere and at every moment, a principle called symmetry. But time crystals suggest that under certain quantum conditions, time itself can develop a texture with natural rhythms that don't align with the smooth, uniform flow we're used to. Some theories propose that if space-time can host structures with broken time symmetry, it might also allow for more exotic configurations like temporal analogues of black holes, where time loops back on itself in localized regions. The implications ripple across physics. Time crystals could serve as ultra-precise quantum clocks, their flawless rhythms immune to external noise. Others speculate they might stabilize quantum computers, acting as buffers against the decoherence that plagues qubits. But the most tantalizing possibility, if time crystals can exist in the vacuum of space, they might represent a new form of matter that emerged in the early universe, leaving faint imprints in the cosmic microwave background. Future experiments aim to scale time crystals to larger systems, probing whether their temporal order persists across macroscopic scales, a finding that could rewrite our notions of time's fundamental nature. For now, these strange structures stand as a reminder. The universe's rulebook is far stranger than we imagined, and time itself might be more malleable than we ever dreamed. Black holes aren't just cosmic vacuum cleaners, they're the ultimate shredders of information, or so we thought. When Stephen Hawking first proposed that black holes evaporate over time, radiating away their mass in a faint glow of particles now called Hawking radiation, he stumbled into a paradox that's haunted physics for decades. If a black hole vanishes, what happens to all the information it swallowed? According to quantum mechanics, information can never truly be lost. It might get scrambled, but it should always be recoverable in principle. Yet general relativity insists that anything crossing a black hole's event horizon is gone forever, its details erased from the universe. This clash between two foundational theories isn't just academic, it's a crisis threatening the very laws governing reality. Enter the black hole information paradox, a puzzle so profound its resolution could rewrite our understanding of space-time itself. One radical solution comes from the holographic principle, which suggests all the information falling into a black hole isn't lost but encoded on its event horizon like a cosmic hard drive. Imagine throwing a book into a fire. The pages burn, but if the smoke particles carried a perfect, albeit scrambled, record of every word, the information would technically survive. Hawking radiation might work similarly, with particles escaping the black hole subtly imprinted with data about what fell in. This idea gained traction when physicists calculated that the event horizon's surface area, not the black hole's volume, determines its maximum information storage, a clue that the universe might fundamentally be a two-dimensional projection. But there's an even wilder contender, the idea of islands in space-time. Recent calculations in quantum gravity suggest that as a black hole evaporates, tiny regions of space-time disconnected from our universe could form inside it, preserving information in hidden pockets. These islands wouldn't obey classical physics, they'd be quantum anomalies where the usual rules of locality break down. Picture a sinking ship. From the surface, it seems gone forever, but if compartments below detach and float independently, the cargo might still exist elsewhere. Similarly, black hole information could escape into these phantom zones, re-emerging only when the black hole fully evaporates, like a message in a bottle washing ashore long after the shipwreck. The stakes couldn't be higher. If information can escape black holes, it implies space-time has loophole structures or layers we've yet to comprehend. Future experiments aiming to simulate Hawking radiation in labs using Bose-Einstein condensates or fiber optic analogs might tease out these mechanisms. Others propose scanning the cosmic microwave background for anomalies that could hint at information leaking from primordial black holes. Each possibility pushes us closer to a unified theory of quantum gravity, where space-time isn't just a stage but an active participant in the universe's deepest secrets. What's truly humbling is how a paradox about celestial graveyards forces us to rethink existence itself. Whether the answer lies in holograms, islands, or something stranger still, one thing's certain: black holes aren't just destroying information, they're revealing the fragile edges of our understanding. From bending starlight to catching whispers of quantum foam, humanity's journey to unravel space-time's mysteries reads like the greatest detective story ever told. These 42 experiments aren't just a collection of data points, they're chapters in an epic saga of curiosity, each one rewriting the rules of reality as we know it. Think about it, a century ago, Einstein's theories were radical speculations. Today, we watch black holes collide by measuring ripples in the fabric of existence itself. The cosmic onion, as it turns out, has infinite layers, and every time we peel one back, we find questions even more bewildering than the answers we sought. Take gravitational lensing, for instance. What began as a quirky prediction that massive objects could warp light like a funhouse mirror has become a cornerstone of modern astronomy. Now, we use entire galaxy clusters as natural telescopes, their gravity bending distant starlight into luminous arcs that reveal galaxies too faint to see otherwise. Or consider quantum entanglement, that spooky connection between particles that defies classical physics. Experiments like the ones aboard the Mischur satellite didn't just confirm this phenomenon, they exposed cracks in our understanding of locality, suggesting that space itself might be a secondary player in the universe's deeper workings. And the tools we've built for this quest, they're nothing short of miraculous. LIGO laser beams sensitive enough to detect a proton's width shift over 4 kilometers. The James Webb Space Telescope, peering back to the universe's toddler years with infrared eyes. Even tabletop experiments like those probing time crystal systems that pulse in perfect rhythm without energy, defying thermodynamics, are pushing boundaries we once thought were immutable. It's as if every time we invent a new way to look at the cosmos winks back with a fresh enigma. What's thrilling isn't just how far we've come, but how much remains uncharted. Dark energy's relentless push, the true nature of quantum gravity, the possibility of extra dimensions, these aren't just plot twists waiting to be uncovered. They're invitations to keep exploring, to stay humble in the face of the universe's boundless creativity. Because here's the beautiful paradox: the more we learn, the clearer it becomes that reality is far weirder, far more wondrous than our boldest imaginings. So what's next? Maybe a warp drive prototype humming in some lab, or a detector catching holographic noise from the edge of space-time. Perhaps we'll finally hear the universe's first gravitational waves from the Big Bang, or decode dark matter's cryptic signature. Whatever the breakthrough, one thing's certain: the next chapter of this story will be written by the curious, the stubborn, the ones who refuse to stop asking why. If that's you, then you're already part of the adventure. The cosmos isn't done surprising us, and honestly, we wouldn't want it any other way.